Oh, B, what's up, man? How'd you do? I adjusted your time, by the way.
6:67.
Just a little bit short. What kind of PBQs did you see?
I seen the one we were talking about last night. And then
Oh, the one we talked about last night?
Yeah. I had 4.
What?
I had there's like 5 or 6 emails you had to read and see if they were legitimate or not, or scam or phishing.
Yep.
That one was pretty. You just gotta just say make sure you check who it's from and all that. I mean, I thought that one was pretty easy.
Yeah.
And then there was
it's either you take no action, spam, or report to something.
Yeah, it was like phishing, spam, or respond, or no response.
Yeah, no response. That means it's a legitimate email.
Yeah.
So you saw the PC and the Xbox one behind the firewall.
Yeah.
And what's the other one you saw?
There was like 7 computers, and they were all having sound issues, or some of them were having sound issues, and you had to configure them to. That one threw me off. I was like, I don't know what it wants me to do.
Okay. Well, since you brought it up, let's talk about it. So what you do is, they're all reportedly having sound issues. There's a process, so there's a vulnerability. There's something that happened to all the computers. So you have to go to all the computers, find all the sound processes, and turn them all off. Then you have to quarantine it. There was a virus or something that's taken over the computer, so you have to quarantine the virus and then disable the sound. And then for remediation, you turn the sound back on for the computers. It's like 7 computers, turn off all the processes, but you're only going to quarantine like 3 or 4. Something like that, from what I remember.
2.
Yeah. You got to quarantine 2 of them. So it's a matter of turning off all the processes. But the second part of that is, well, which ones are you going to quarantine? The ones that are infected. And you have to click on the right ones. So be prepared to see that one. You have to use your task manager or your processes to find out what's running. Yeah. What's the other one you had? That's 3. Was it the chat?
Yeah, the chat.
Yeah, the chat. Yeah. Pick the right responses for the customer.
Yeah, I mean, that seemed like common sense, though. Like, just be nice and, I don't know.
Elaine says, any familiar ones from the final exams? Any questions?
They're similar. Trying to think. I don't remember exactly which ones there were, but I had a few on the some threats like malware and stuff.
Oh, okay. Okay.
Do you see any change management stuff on there?
Yeah,
Yeah.
I got a couple of those.
Yep. I figured those were gonna be on. Risk.
Risk. I don't remember any risk ones.
Okay. Ports.
No, not except the when you pick the port for the PBQ.
Oh, for the Xbox 3389.
3389, yeah.
Oh.
Yeah. Okay. All right. Pretty decent. Yeah, they got rid of a lot of new stuff on this new exam. I thought the newer exam was easier than the preceding one. 11. 12 has got a little lighter. I thought it was better. Yeah, but it's good stuff. Thanks for sharing. And thanks for getting that uploaded when you can. I'll check and see.
Years, but as you have seen already with the A plus is good for 3 years after you earn your cert, and then they expect you during that 3-year time frame to renew it in some way.
That plus exam will be exactly 3 weeks from today.
You can renew by taking the exam again. You can renew by taking
Yep,
a higher level
3 weeks
exam.
from today.
There's lots of ways to renew your cert, but they want you to be able to renew and keep the latest information in your brain. They want you to know what the latest technologies are and be able to keep up with those. So obviously, the certifications I got years ago, it's interesting to talk about, and to some degree, they are not worth very much. But here's where
I will drop in the
So I mentioned
GIF.
that I got an MCSE. This is a certification
There's a GIF for that.
Microsoft has not offered for a very, very, very long time. The Microsoft Certified Systems Engineer.
Where is it at?
And
Let me see.
you have to take 6 different certification exams surrounding the use of primarily Microsoft Windows and Windows Server. So it was everything you need as a foundation to be able to support Microsoft technologies.
There you go, Mr. T.
Enterprise, Active Directory, the networking side of things, the desktop administration, being able to maintain those systems, to automate the maintenance of those systems, to push out your patches, to have automated installation processes, everything you need to be able to manage Windows. Well, those were based on, when I took those exams, those were based on Windows NT. That was when those were out. We think, well, what good is that now? Because that was Windows NT. It's not good anymore. That certification's long gone. What a waste of time. Except a lot of the fundamental skills that I learned going through the MCSE are still in Microsoft Windows. So understanding Active Directory. It's the same Active Directory that we have today. There's obviously a number of newer features associated with it, but the foundational knowledge you need to be able to understand how Active Directory is structured, how it works, how you integrate with it, how you can access it, how LDAP integrates with it, how people are able to log in and use it, the type of group policy that you can configure, all of those things are identical today as they were 20 years ago. So as you are going through these courses and you're learning about a very specific version of Windows, Windows 11 on the latest A+ exam, those skills you learn with Windows 11, you will be able to apply in some degree towards Windows 12, towards Windows, well, they have a Windows 13. You think they'll do that? Maybe Windows 14? Whatever they end up calling it. Or are they calling it, I think they're calling it the name of the year now, aren't they? Are they going to move to that? So whatever they come up with, when they come up with the Windows 2025, Windows 2026, Windows 2027, it's probably not a bad idea. Whatever the scheme they come up with, in the future, you'll be able to look back 10 years from now and think, I'm glad I learned that because I'm still using those skills. Same thing especially applies for networking. The Ethernet frame types that I learned at the very beginnings of my technology career are the same Ethernet frame types that we're using today. The same process for capturing frames and viewing them and looking at a protocol decode, identical to what we are doing today. So we often go into these certifications and thinking about this as, how can I get the cert so I can get a job? We often forget, how can I get the cert so that I now have a foundation of technology that I can build on as I go through my career? There is value to these certifications that you will continue to use and to benefit from as you go through your entire IT career, which is interesting and remarkable and makes you understand a little bit better how important these certifications might be. So from my perspective, certifications, I don't have to take certifications anymore because this is what I do. If somebody showed up and said, well, you can't put things on YouTube unless you have a certification, I'm going to go get that cert so I can post those videos on YouTube. So we'll have to see what that ends up looking like. Let's keep going through this list of things that you have. We've got lots of questions that are coming in. Thank you for submitting those. I know we've got about 10 minutes before we get to our hard stop at the top of the hour. So let me pick a couple of good ones as you are coming through this list. Here's one that's pretty good. This is one I'm going to also sort of modify your question in a bit. This is from Ian. Eon says, good afternoon, Professor. I graduated with my bachelor's in IT in December 2023. Now, by the way, I'm very curious about those of you that have gone through a 4-year degree that specifically was an IT degree. I would love to hear more about where you did this because I try to keep up with different colleges and universities. It's hard to find a degree, a bachelor's degree in IT that really is focused on IT. I'm starting to see a slow move in the industry, in the world of higher education. I'm going to use that term loosely. But that is one where they're getting us a little bit better with really focusing on IT in those 4-year degrees rather than simply calling it computer science, which is not IT, by the way. Not even close, not even related, as it turns out. Very little. So, and Ian says, I went to FIU. So, Florida International, a great university. Also, I have some great stories about networking at Florida International and how their oceanography building, I'll bet even today, still has coax 10-base 5.
All right, everybody, let's take 10 minutes. See you when you get back.
I bet they still do because it was they put it in the bricks of that one They still have this enormous, that's a thick net, they call it. They have a thick coax in that thing. Anyway, I will go look at theirs and see what they have there. I'm very interested in that. Anyway, the question is, I currently work as a repair technician / triage agent at Geek Squad, but with appliances and TVs. How can I translate this job to relevant IT or transition to we're not specifically dealing with the computers, operating systems, tablets, phones type things at Geek Squad. You are getting the most important part of the Geek Squad experience, which is you're working with the general public. You are learning computer skills to some degree, because obviously you have to learn how to connect to wireless networks and network these televisions that we have these days. They've turned into their own computers. But the other thing that I find with this is the customer service side. That customer service piece is so important in IT. What? I thought we worked with computers. I thought we worked with servers and tablets. This computer has nothing in it from a customer service perspective. It's all ones and zeros. Why would customer service be important? Well, because somebody's holding this tablet. Somebody's trying to use this tablet to accomplish something. They're trying, in the world of Best Buy, they want to have a computer television where they can talk to their family. They can have a video conference with family members, or they want to be able to send emails to people that they know. They want to be able to text message. You know, it's very, very, not relatively simple, because it's the same things we're doing in our corporate world, but it's very consumer oriented. That is the most challenging customer service you're going to have. So I would highly encourage you, although we often complain about needing to deal with customer service, I would recommend you turn that around a little bit and soak in as much of this as you can. The better you get with working with other people, finding out what their problems are, working them through the stressful and sometimes angry feelings that they have about making the system work, and you're able to turn all of that around and bring them to a place where their problem has been solved and they're now much happier, that's a great place to be. And it's a process you're going to not just want to go through, you're going to need to go through that process with every single interaction you have in the world of IT. And I will tell you, from the people that I have met and the places that I have worked, the better you are in working with people, the better technologist you tend to be. Super important, sort of in the world, but especially in the world of technology. Because you have to be the person who not only solves puzzles, and that's what we do as IT professionals. We are puzzle solvers. If you're someone who loves the find a word, you love an anagram, you like the notograms, you like the Sudokus, you're one of those fix the puzzle kind of thing, you want to figure out the answer to that puzzle, that's what we do every day. Somebody shows up with a puzzle, and then we have to figure out this highly complex series of tasks to be able to solve the puzzle. That's what we do. And I think a lot of people in IT are really driven by the problem-solving aspect of it. But if you really want to excel, and you really want to do well, and you really want to propel yourself through the world of IT and make more money and have more responsibility and do other things with other companies, you really want to work on the people side. It will return to you a benefit in spades. There will be a multiplier benefit of being able to work well with people. The part that I really discovered about that in this particular role, especially in the internet, it may be hard for you to believe this. Sometimes people on the internet can be a little bit mean. So you really have to create kind of a thick skin to put your face on the internet. And so what I really discovered a number of things about me is I'm pretty good about ignoring that. You really get to a place where initially it hurts when people start doing that, but then you figure out, okay, how can I compartmentalize this? How can I create a bark skin for myself where they say something but they're not really saying that because they don't like me personally. They don't even know me personally, but they're frustrated with something else. Or they're having to deal with learning all of these things, or they hate memorizing port numbers, and they take that stress and that frustration and they put that on someone else or something else. And so I get that. You want to say bad things in an email to me, you can do it all day long. Doesn't bother me at all. I read through it. I try to figure out, is there something else here that I'm missing, or are they just being spiteful? Sometimes there is that. And then once I figure out what to reply back and say, here's how I think I can help you, or in the cases where they're just being mean, just ignore it completely. You don't engage. That's really the secret on the internet, by the way, is you just leave them hanging. You leave them unread, and they hate that. Hate it. So more than anything, if you want to make somebody angry on the internet, you just ignore them. And it's remarkable how powerful that is. Never engage. But if you are able to connect with them at a human level, they're really looking for help, and they don't know how to ask for it the right way. Well, let's see if we can redirect that a little bit. Those skill sets are extremely valuable financially and for a career perspective. They are very, very, very valuable skills. So at a very minimum end, being able to work at Best Buy and being able to you're not going to be there forever. Nobody's at Best Buy forever. Very few people. The CEO definitely not at Best Buy forever. So you're going to want to soak in as much of this as you can. You want to keep your eyes open. You want to see how people are handling things. You want to think about how you could be doing that even better. And eventually, you'll also want to think about the technology side of things. The things you are learning about connecting televisions and appliances these days. Every appliance in my house is now connected to the internet in some way, or better, or for worse. Well, if you can have an app that gives you a status on your washer and dryer, on your oven, on your microwave, on your coffee maker. This is what's in our homes today, on our refrigerator. Do we need connectivity for a refrigerator? No, we do not. Do we have technology and connectivity in our refrigerator? Yes, we do, which means we have to know how to support that. Just because you don't agree with it, and maybe I don't agree with it, doesn't mean somebody else doesn't want this. So you can be the one to figure out that technology, understand, why am I putting an IP address on this? Why am I setting it for DHCP? What does the default gateway mean? What does that subnet mask have to do with any of this? Why can't I get connectivity to the internet? All of that, those basic network troubleshooting skills, you will use for your entire IT career, regardless of what you do. You work with databases, you need to know that. If you're in the cloud, you need to know that. If you work in a data center, you need to know that. If you work on operating systems, you need to know that. Are you a network person? You absolutely need to know that. So all of these things that you will be working with and the things that you do, even in the world of Best Buy, will help you a great deal. My first customer service related job was at a company when we would watch movies back in the day is we would go to a place that had tapes and tapes of movies, all the latest blockbusters. We could grab the Die Hard, we could get the Terminator, we could go get the Star Trek, we could get the tape, we would take it home, and we could put it into a machine that would then show us that video, that movie. It's archaic, I get it, but that's what we had. There was no internet. And I worked at the place that rented those movies. First I got movies for free, which was awesome, especially, but on Saturday nights, not so good, because everybody would just sell out the place on Saturday. I worked or lived in a very small town, in a very small county, and this was big entertainment for us. It seemed like everybody in town would show up at the video rental place on a Saturday because we were closed on Sunday, because you get that extra day of rental out of it. They'd walk out with a stack of 10 tapes, and they take it home, they bring it back on Monday. I will tell you, you need to be kind and rewind. It's just something I want to have you take back with you. Pretty important. It was a movie gallery, for those of you wondering in the chat room. It was not Blockbuster. It was the movie gallery. And national organization, but it was one where you worked with people. You got to talk to people. I lived in a small town. It was all in the South. Small towns in the South are, how you doing? How's Becky? How's she feeling? How's her hip doing? She doing good? I'll stop by later. I got some plenty. Just came out. We got a bunch that we put in. We'll bring it over to her. She loved it. So that's what we did. And that was my first chance to figure out what I knew and didn't know about customer service. There wasn't a lot of technology there. So I feel like I'm almost in that same type of role you're in, Ian, where I had to figure out, okay, I can connect things up. There's coax, and there's power, and there's some basic troubleshooting, but it's not computers. The computers really were interesting to me. So I sort of used that, propelled that. By the way, that was before we used computers in the rental store. We did everything on paper because computers were too expensive for, I know, super old. That's the way it works. When you get databases on, how valuable having that data in one place is. So those are the types of things that are jobs that at the time, you might not think this is very valuable in the world of IT. Turns out some of the things you learn can be extremely important and working through those. So translating that job to a relevant IT or transitioning to entry-level help desk, that should be a relatively simple move, almost a lateral move from what you're doing, because we can teach you the technology. We can have you understand how an operating system works. We can train you on what to do when you get a blue screen of death. We can help you understand how to get data on a USB drive and take it to another person. We can train you on all of that. The part that's hard to train on is the people part. That I think is the hardest part to learn. And you are learning that in spades. So for those of you that have been through that, I think my very first job had nothing to do with technology at all. It was working out in the fields. I came from a very small town. It was very agricultural. So a lot of what I did in the summers was working with a hoe in my hands. I got gloves on, and we're just out there in the field all day. It was just menial labor. And that was one where you start to recognize technology could be pretty useful. First, it's air conditioned. Gotta love that. And I think working with technology is a great way to move up and move up quickly in better than almost any industry you're going to run into. So another thing that you can. I know we're probably hanging out. We're doing okay, and working through that. Let's go through the other piece of that. So let's talk about exams and studying for exams. This is something that's come up a couple of times. This is one that asks, Professor, what's your ideal study duration when you were studying for your exams? Any unhinged tips? Nothing unhinged. I think it's a fundamental. We've taken what we think is the right mix and type of study to give you the best possible outcome. And it really consists of 4 different things. We think it is useful to be able to have these 4 different elements as part of your studies. You don't have to have all 4 of these, but it helps to have all 4. The first is we think it's useful to be able to have a good book and be able to read some of the information associated with these technologies. It's also we're talking about a certification that will cost you many hundreds of dollars. So getting a book for $30 or $40 is pretty good investment, especially considering all of the information that's contained within that book. So reading a book's a great thing to do. Watching some videos. Really, I start with the watch video part. We refer to this four step or 4 elements as WRAP, W-R-A-P. The watching of the videos is the W. Watching videos gives you a demonstration on the screen. You can see someone doing it. You get a little bit of lecture, you get a little bit hands-on without having to touch anything. You can see someone else performing the paint. You can see someone else doing the installation of Windows. You can see someone else troubleshooting that particular problem. So there's that watching part of it. The reading part, we'd already mentioned with the book, that's the WR and the RAP. The A is applying what you have learned with the videos and the books, get some hands-on. So if you're working on some labs, that is applying that knowledge for you to do some hands-on. And we have labs on our website that might be a good choice for that. And then lastly is the P, the RAP, the practice that you're going to do. Practice questions should come last. There are people that we've talked to on our Discord that think you should start with practice questions. Forget the books, forget the videos, let's just go to practice questions. But in reality, it's not your best way to go through, about doing this. You need to have some perspective of how you're answering these questions. The questions aren't there to teach you. The practice questions are there to see if you've learned what other things have taught you. I think that's the best use of practice questions. Now, if you don't get questions right, there's the opportunity to learn. But why would you get every question wrong? That doesn't give you any feedback on how you're doing so far. So I think that's the important part of being able to understand all of those scenarios and working through them. I think it's an important part of studying for anything is being able to use all four of those different learning opportunities. Watching the video, reading the book, applying it with labs, and finally practice with practice questions, the RAP. Those are the four things that I think would be it's not really unhinged, it's very the learning process. And we try to emphasize those on our website constantly. We're going to be doing a lot more of that RAP method so that you can be sure that you have all the tools you need to be successful with these certifications. And if you're somebody working through certifications and trying to figure out what should I do in this world of IT, how am I going to get through? If you've looked at the exam objectives, they're enormous. And you may be thinking to yourself, how am I ever going to get through all of these different bullets? How am I ever going to learn all of this content? By the time I learn this one, I've forgotten it when I get to the next section. Well, you think you've forgotten it, but you really haven't. It's really in there. You just need to know how to use these multiple methods to learn it in different ways. And I think that's where we start to miss the opportunities. We think watching the videos is it, and you're done. But I've never said that you should be learning that way. It's only one dimension. You need to add on a different set of synapses firing for similar content. So if you watch somebody installing Windows, and then you read about the Windows installation process, you're learning twice in different ways, and very often with different types of content. So don't think you can dismiss one of those and never have to read a book. Now, obviously, if reading is difficult for you and you find it easier to watch a video, watch more video. Watch multiple video series. So there are ways where you could get rid of one of those, but add on additional of the others. So another example of how you might want to use different methods. It's sort of like the idea of having those different touch points whenever you're thinking about going to a movie. You see the movie advertised, you saw a trailer come up on YouTube, you saw a show where somebody in the movie was interviewed, and then somebody else saw the movie and told you about it. So you got three different places where people are telling you about this. After a while you think, okay, I think I understand now about this movie and what they want me to do. Same thing applies with these exams. Watch the video, then read a book about it, then maybe do some labs. You're doing the same thing 3 times, but in different ways and with different types of content. It starts to stick. You really start to understand it, and it starts to get embedded into your brain. And for something like a certification exam, that is a great place to be. And now you can take the practice exam and see if you really, really understand. Another way to go about doing that. That's our RAP method. That's how we think you should be studying for the exam. That's the way that we think is going to serve you the best. You find the right combination for you. You find the right set of tools for you. You put those together. You've got a formula for success. Well, that brings us to the end of another study group, 2 hours plus of information. Hopefully that's given you something to think about for your studies, and maybe you've learned something as we've gone through all of this today. Of course, we do one of these study groups for Core 1. We do another one for Core 2, so if you like this study group, come on back Thursday. We've got our Core 2 study group, and then we will absolutely have another set of brand new questions to go through, and a number of questions we will go through in the after show. We would love for you to join us on Thursday for that. And of course, next week is our Network Plus study group. The week after that is our Security Plus study group. There's always something to think about, something to learn, and always something fun to do. So that's another place where you can meet us. Come on back Thursday. We'd love to see you there. In the meantime, we will be over on our Discord at professormesser.com/Discord, helping with folks that are studying for their A+, Network Plus, Security Plus, and so much more. Thank you so much for joining us. We will see you next time on the A+ study group. Thanks, everybody.
Grammarly now uses AI to help you write. Not just revise. Type a prompt and generate a...
Hello, everyone. I'm James Messer. Welcome to Professor Messer's N10009 Network Plus training course. In this training course, we'll take you through everything you need to know to pass your Network Plus exam. CompTIA, of course, is one of the largest certification bodies in the world, and regardless of why you're taking this exam, I think you'll find there's something here for practically anyone in information technology. If you're working on moving up the ranks within IT, then the Network Plus exam provides you with information you'll need across many different areas of these technologies. There are also organizations that require you to have certain certifications, and Network Plus might be one of those. But even if you're not taking this for a certification or to even take the exam, there's still a lot of great information in this course that can help you with your IT career. CompTIA stands for the Computing Technology Industry Association, and it is one of the largest vendor-neutral IT certification entities in the world. CompTIA certifications cover everything from basic IT all the way into detailed cybersecurity topics. And the members of CompTIA consist of resellers, distributors, IT training organizations, and many other companies that are focused on information technology. These are also certifications that are recognized around the world. These exams can be taken in over 100 different countries, and there are many different languages to choose from. If you found your way to this Network Plus training course, you may already be familiar with myself and the training courses that we provide here at Messer Studios. Personally, I have been in information technology over 30 years with jobs that range anywhere from supercomputer operations through systems engineering, network analysis, network troubleshooting, and finally, cybersecurity engineering. If you're looking for someone who is well-versed in the intricacies of the technology, the industry, and what employers might be looking for, then you've come to the right place. If you look at our video course, you'll notice that there are a lot of individual videos. Those videos tend to be less than 10 minutes apiece. That way you can find exactly what you're looking to learn, focus in on those individual topics, and then if you need to watch some more, you have another 10 minutes available. Or you can stop right there and step back into your studies at any time. Our goal is to create a video series that is the highest quality possible. This means that we focus on providing you with content that's valuable, focused on the exam objectives, and gives you exactly what you need to know to pass your exam. Our goal is to give you the skills and knowledge that you need to get your first job in information technology or to move up within IT to get an even better job. If you're watching this online, then you've probably noticed that there was no registration, nothing's hidden behind a paywall, and that our entire course is available for you to watch online for free. So your natural question might be, What's the catch? Is there something that we have to do to be able to gain access to this information? And the simple answer is no. Everything is available for you to watch online for free with no limitations at all. If you want a version of this course that's available offline, we have downloadable versions that you can purchase, and we also have other supporting materials that might help you throughout your studies, including our course notes, discounted vouchers, and much more. If you want to find out more about exactly what's available, all of it is on our website. Simply visit ProfessorMesser.com. We never remove our training videos from YouTube, so you can go back a number of years to find different versions of our Network Plus course available. So how do you know if the Network Plus course you're watching right now is the latest version? Well, the N10009, which is the version of the exam that this series is based on, was released on June the 20th of 2024. We know that CompTIA tends to keep these courses available for about 3.5 years. That means that this series of the Network Plus exam would probably retire somewhere around the end of 2027. So if you're watching this video within that time frame, then you're probably watching the right version associated with the N10009 exam. But of course, the CompTIA website is the best place to go to determine what the latest version of the exam might be. So if you have any questions about which exam version you should be watching or which video series applies to you, make sure you check the CompTIA website. To earn your Network Plus certification, you need to pass a single exam. This exam is a 90-minute exam, and you get a maximum of 90 questions. You might get fewer than 90 questions on your exam. The passing score you're looking for is a 720, and this is on a scale between 100 and 900. The exam itself consists of 5 different domains. Domain 1 is networking concepts, and that consists of 23% of the exam. Domain 2 is network implementation at 20%. Domain 3 is network operations at 19%. Domain 4 is network security at 14%. And Domain 5 is network troubleshooting at 24% of the exam. If you're following along with our video series, I would highly recommend that you also download a free resource from the CompTIA website called the CompTIA Network Plus Certification Objectives. This is a set of exam objectives that will tell you everything you need to know before you walk in to take that exam. You can find a link to these objectives from the Professor Messer website at professormesser.com/objectives. All of the videos in this course follow these objectives in the objective order, so it should be relatively easy to find exactly what you're looking for during your studies. I would also recommend that you get a good book on Network Plus, and we have recommendations on our site that can help you with your studies. There are also many people that are studying for their A+, Network Plus, Security Plus, and other certifications, and you can talk with them directly on our Discord at professormesser.com/discord. There are a lot of people studying for their Network Plus exam, and on our Discord, you can start or attend any ad hoc study session at any time. We also have other resources that can help you with your Network Plus journey. You can find those available on our website at professormesser.com/netplus-resources. So now you've got all the training materials you need to be successful with your Network Plus studies. We have our entire course available on our website for you to watch at any time. We also have our 24/7 Discord chat. We also include monthly live study groups. So if you'd like to join us for some interactive Q&A and your chance to ask any question that you would like in our after show, you can find those available on YouTube as a replay at professormesser.com/YouTube. And if you check our calendar on our website, you can join those sessions live. Now you've got everything you need to be successful with your Network Plus studies. Our video course, additional resources on our website, an entire community of people that are studying to get their certifications, and so much more is available on our website. Visit professormesser.com and join us in the next video as we begin your process through your Network Plus certification. Best of luck with your studies, and we'll see you in the next video.
I'm not really one for the spotlight, but there is some gravy to be had. You know, I always seem to get primo parking.
We'll start our Network Plus course with a broad discussion of something we refer to as the OSI model. This is referring to the Open Systems Interconnection Reference Model, and it's a model we use in IT to describe the process that data takes as it traverses our networks. The OSI model is not designed to be a detailed description of this data, but instead is intended to describe a broad overview of how data traverses our systems. We're also not describing the OSI protocol suite. Indeed, most of the protocols we use today are based on TCP/IP, but the OSI model is one that we can apply to many different protocols, and it works perfectly with the TCP/IP protocols that we use today. Also keep in mind that there are many different protocols that might operate at an individual layer of the OSI model. So as we step through an individual layer, keep in mind there might be tens or even hundreds of protocols that might exist and work at that particular layer. By understanding this OSI model, we can converse with other people in information technologies in a way that we would all understand. It doesn't matter if they're working inside of your own company or with a different organization. When you mention OSI Layer 7 or OSI Layer 4, everyone understands what that means and what effect it has on the overall operation of the network. If we start at the top of the OSI layer or OSI Layer 7 and work our way down to OSI Layer 1, we have Layer 7 being the application layer, Layer 6 is the presentation layer, Layer 5 is the session layer, Layer 4 is transport, Layer 3 is network, Layer 2 is the data link layer, and Layer 1 is the physical layer. There are many different mnemonics that people use to memorize this, but if you start at the top and work your way down, you can take the first letter of each one of these layers, and you might have a term such as, all people seem to need data processing. That's application, presentation, session, transport, network, data link, and physical. Let's start our conversation of the OSI model at the bottom of the OSI model, or Layer 1. We refer to this as the physical layer because it's describing the physical signals that we send through the cable and fibers on our network. At this layer, we really don't have many protocols to speak of because we're really just talking about getting a signal from one part of the network to another. When we refer to a physical layer problem with the network, we are referring to the OSI Layer 1 physical layer. This means that we might have a bad cable, a bad fiber, there might be interference on a wireless network, and it may require us to do a series of tests to determine if we are really able to get a signal across this particular wire or this particular fiber so that we can keep this network running. A lot of the troubleshooting that you do at Layer 1 is running loopback tests, testing cables and fibers, and checking different adapter cards and other devices to make sure they're working properly on the network. One step up from the physical layer is Layer 2, the data link layer. This is the fundamental layer that's used to communicate between two devices on the network. We often refer to this as the MAC address layer because that is the data link control layer, or DLC layer, that is commonly associated with the network cards that are in our devices. And most of the time, these are Ethernet adapters or wireless adapters, and we refer to that physical address on that device as the data link control address, or the MAC address. In this case, MAC address is not referring to an operating system, it's referring to the media access control address. So anytime you hear someone talk about a MAC address, they are referring to the hardware address of that particular adapter card. Since the network switches that we use on our network determine how to forward traffic based on the destination MAC address, this is a layer that we often refer to as the switching layer. So anytime we're referring to a MAC address, a problem with a switch being able to operate, or anything else that may be associated with this particular hardware address, we're referring to OSI Layer 2, the data link layer. The next layer up is OSI Layer 3, or the network layer. We often refer to this as the routing layer because this is the layer that routers use to determine how to forward traffic. And they are specifically looking at the destination IP address in order to determine what the next hop might be for traffic traversing the network. This is also the layer that we're able to fragment these frames into multiple pieces, especially if we're sending it across a network that may require smaller frames than what is on our local network. So we can cut those frames up into smaller pieces to be able to fit them through the network and then put those pieces back together on the other side. Anytime we're referring to a problem relating to IP addressing, subnet masks, anything related to an IP address, or anything about routing, then we're probably referring to layer 3, the network layer. Layer 4 is the transport layer, and as the name implies, we're referring to the ability to transport information from one device to another. You might also refer to this as the post office layer, because this is responsible for getting your letter or your information from one side of the network to the other. The protocols that are often used and operate at layer 4 of the OSI model is TCP, that stands for Transmission Control Protocol, and UDP, or User Datagram Protocol. These two protocols are commonly responsible for getting all of the information within our IP packets from one device to the other. In many cases, this involves taking a large amount of data, putting it into smaller pieces to be able to get it across the network, and then putting those pieces back together on the other side. Before we can send that information from one side of the network to the other, we may need to create a session so that a device is able to receive that data. Layer 5 is the session layer, and it provides communication management between point A and point B. Anything relating to the initiation of a session, stopping the session, or restarting the session can commonly be associated with that layer 5 session layer communication. If an application is using some type of control protocol, or you're tunneling information within existing data, then you're probably using OSI layer 5. OSI layer 6 is responsible for putting all of this data into a format that we will eventually see with our human eyes. This refers to character encoding, application encryption, and decryption, and it's often combined and discussed in conjunction with the application layer at layer 7. Layer 6, or the presentation layer, is the layer that is commonly in operation just prior to us seeing this data on our screen. And the top layer of the OSI model is OSI layer 7, or the application layer. This is the layer that we see on our screen. So anytime that we are interacting with an application, we are operating at layer 7 of the OSI model. Common applications that would operate at OSI layer 7 are
How are you doing?
and HTTPS, FTP,
Number
DNS,
one,
Common
let's
Read,
go.
and thousands of other application protocols.
I'm
That's
looking
a
at the
broad
pronunciation
overview
of your
the
name to
OSI
see if
model, but how do we fit things in the real world into each of
Is
these
it
layers? Let's
Malikarjan
start down at the
J?
bottom with layer 1,
I'm not
or the
sure if
physical
I'm
layer.
pronouncing
When
that
we refer
correctly.
to cables, fiber optic connections, the signal going across those connections, or a wireless network, then we're operating at OSI layer 1, or the physical layer. When we refer to OSI layer 2, or the data link layer, then we're talking about Ethernet frames, MAC addresses, or addresses referred to as Extended Unique Identifiers, or EUI. There are EUI 48 addresses and EUI 64 addresses, for example. And as we described earlier, anytime we're referring to the switching process, we are referring to OSI layer 2. At OSI layer 3, or the network layer, we're referring to IP addresses. So anything that has an IP address or subnet mask, or referring to the way that routers forward traffic, all happen at OSI layer 3. If you're referring to a TCP port or a UDP port, then we're operating at OSI layer 4, which is the transport layer. At OSI layer 5, or the session layer, we're using control protocols to start and end different sessions, or we may be tunneling traffic using protocols that operate at OSI layer 5. We often associate the encryption of application data with OSI layer 6, or the presentation layer. So if you're communicating to a website and you're using SSL or TLS to be able to encrypt and decrypt that data, that process is occurring at OSI layer 6. And at OSI layer 7, or the application layer, is where you are interacting with the application itself. Anything that you're seeing on the screen, the application itself, or any messages from the application are often referred to as layer 7 information. If you wanted to drill down a little bit further into the OSI model, you might want to capture some data on your network and view that data inside of an application such as Wireshark. I have a Wireshark protocol decode on my screen where I've captured data on my network, and this Wireshark has 3 separate windows that is displaying different views of the same data. The top window is a frame-by-frame breakdown. For example, I have highlighted frame 88 on this top window. The middle window describes more detail of what different information is contained within that single frame. And on the bottom window, we have a hexadecimal and ASCII breakdown of the data itself. Let's focus our view on this middle window, which is a summary of this highlighted frame 88. You can see that there are 5 different lines of data inside of this single frame, where the protocol decode has separated out the individual protocols within this single Ethernet frame. Let's start with the one at the very top, which describes frame 88, which has 2005 bytes on the wire, and 2005 bytes were captured by Wireshark. If you wanted to associate that line with the OSI model, that would be best associated with layer 1, or the physical model. Next down is Ethernet 2, which has a source MAC address and a destination MAC address. And since we are describing MAC addresses, everything within that line of the Wireshark decode is associated with layer 2 of the OSI model, or the data link layer. The next line down describes the Internet Protocol, or IP. And as we described before, IP fits squarely in layer 3 of the OSI model, or the network layer. And in fact, there are individual IP addresses listed here for the source IP address and the destination IP address. And you can see there is a DNS resolution here that shows that the IP address of 72.14.247.19 is also associated with googlemail.l.google.com. As we move down this list, we're moving up the layers of the OSI model, and the next one is the Transmission Control Protocol, which means we're communicating via TCP for this Google Mail communication. Since TCP is in this list, we must be at OSI layer 4, or the transport layer, and indeed you can see TCP port numbers for the source and the destination of this traffic. Since the destination port is port 443, Wireshark has already filled in that we're communicating over an encrypted channel using HTTPS. And if we go one layer down into the secure socket layer, this effectively encapsulates the top 3 layers of the OSI model. So secure socket layer and everything underneath it are referring to layer 5, the session layer, layer 6, presentation layer, and layer 7, the application layer. Here's a summary of that protocol decode broken out into the different layers of the OSI model. We had electrical signals at the physical layer. Layer 2 at the data link layer had Ethernet frame information. Our IP addresses were at layer 3, or the network layer. Our TCP encapsulation with our TCP port numbers is at the transport layer. Our session layer linked the presentation information to the transport. Presentation layer was obviously performing that SSL or TLS encryption and decryption. And layer 7, or the application layer, is referring to that Google Mail front end and being able to send and receive emails using mail.google.com. Hopefully you're now able to see how this very broad description of an OSI model can be applied to practically any communication that's occurring over the network. And this allows us to talk with other IT professionals and communicate in a way where everyone understands exactly what we're referring to when we talk about a layer 1 physical problem or a layer 7 application problem.
More boxes, more options. Granger has over 1,700 box types in stock, and ready to help you pack, store, and ship everything. And you can count on Granger to deliver your boxes fast. Count on...
If you were to walk through a data center, you will see many of these racks all together with a lot of different equipment installed in each one of them. All of these devices work together to be able to take data from one part of the network and move it to another part of the network. Each of these devices is installed for a specific reason, and it's helpful if we understand why we installed that particular piece of equipment to begin with. Over time, we may be installing more of this existing equipment into our racks, or we may be installing new technology. So in this video, we'll look at different types of devices and how we might use them in our data center. Let's start with one of the most common devices that you'll find, which is a router. A router allows us to take data on one IP subnet and route that information to a different IP subnet. These may be subnets that are next to each other in the same data center, or these IP subnets may be located in different parts of the world. We refer to a router as an OSI layer 3 device. At the OSI layer 3 or network layer, we're referring to IP addresses, and IP addresses is exactly what's used by a router to be able to determine the next hop for this information. You may sometimes see this routing functionality also included inside of an existing switch. And we often refer to these as layer 3 switches, which of course is referring to that OSI layer 3 functionality. It's not that the switch itself is now operating.
Everybody good to go?
OSI layer, it's just within that same piece of equipment, we have both a layer 2 switch and a layer 3 router, so we've abbreviated that as a layer 3 switch. These routers often connect many different types of networks. So we may be connecting a local area network, or a LAN, to a wide area network, or a WAN. These might also be copper-based connections or fiber-based connections. So we may have routers with many different connections or interfaces on them, and we're connecting many different diverse networks to all of those different interfaces. Another common device is a network switch. Switches operate at the MAC address layer to be able to forward traffic, so we'll often refer to that as an OSI layer 2 or data link device. These operate mostly in hardware. The hardware inside of these devices is referred to as an ASIC, that is an application-specific integrated circuit. There are many different functions and capabilities inside of these switches, especially if you're using one designed for the enterprise. For example, many of these switches have the ability to include power on the same wires as your Ethernet connection, and we refer to that as Power over Ethernet, or PoE. And as we mentioned before, you may hear folks refer to this as a layer 3 switch if the switch includes some type of routing functionality built into the device itself. Security on our networks is also important. That's why you probably are using a firewall at home, and you most certainly have a firewall in your office. A traditional firewall allows you to filter traffic based on a TCP or UDP port number. But if you have a more modern firewall, you're probably using a next generation firewall, or NGFW, which is able to identify applications traversing your network and allow you to manage whether that application should be allowed or not allowed on your network. Most firewalls also have additional functionality. For example, it's common to find firewalls that will allow us to encrypt traffic traversing the network through a virtual private network, or VPN. It's very common to have a firewall at one remote site and a firewall at another remote site, and be able to create an encrypted tunnel between those firewalls using this VPN functionality. And most firewalls can also operate as a layer 3 device, which means the firewalls themselves can act as a router. That's because they are often sitting right between the ingress and egress point of your network, where all the traffic on the inside of your network is going to the outside or internet connection, and your internet traffic is coming inbound to your local network. We rely on the firewall to be able to manage the communication between the inside and the outside of the network. To be able to perform this functionality, many firewalls also provide network address translation, or NAT. And because they are a router, it's very common to have dynamic routing protocols supported inside of the firewall as well. Many data centers might also have standalone IDS or IPS devices, although much of that functionality is also integrated into the more modern next generation firewall. IDS refers to an intrusion detection system, and the IPS refers to an intrusion prevention system. Both of these work in similar ways. They're looking for attacks that are inbound to your network and are able to identify, alert, and in many cases prevent that attack from gaining access to your network. These are commonly known attack types. These might be exploits against
Musa,
operating systems
you
or
said,
applications that you're using, and they
where
might take
do
advantage of
I study?
vulnerabilities with those applications or systems.
So I'm
Take
currently
advantage of
doing
overflow,
online
scripting
courses.
vulnerability,
So
or
courses
other
that you can take at
vulnerabilities to
multiple
those
different
systems. If you're using an intrusion
multiple
detection
different
system, it's
sites
able
or
to alarm or alert if it ever sees
online
any of these
academies.
inbound attacks. If you're using an intrusion prevention
Cisco,
system, It's able to
Networking
go a step
Academy.
further and
You can go
block
there
that
to do
particular attack before it gets inside of your network. Since
cybersecurity
an
courses,
intrusion
or you can go to
detection system is
CompTIA.
not able to block that traffic, it's very common to see an intrusion prevention system used on our enterprise networks. If you've ever used a website that may be accessed by millions of people every day, you may be wondering how that site is able to remain up and running without any type of downtime. In most cases, it's because that site is using a load balancer to be able to distribute that load across multiple physical
Yeah, it's
servers.
pretty good. These
As
are
the end user,
these
you
are
have
good
no idea if
certifications,
this load balancer is
especially
in
it's
place.
in the
If you were to
IT.
look at the data center for this organization,
It's in the IT
you
career
might find
field.
a large number of web servers or database servers.
It pays
farms
very
that can
well,
be used in
and
conjunction
it's
with
something
this
that
load
you have to
balancer
use in
to
your
maintain
everyday life.
uptime and availability.
So
These
tech
load
is the
balancers are
future.
also
So
very
every day
good
you're
at
using a
identifying
computer or your phone.
outages to these
So you can
servers.
use it
So if one
just
of the
not just on the
servers
job,
happens
but
to
in your
fail
personal
due
life
to a
every day.
hardware error or some type of software problem, the load balancer can recognize the issue, take that server out of the rotation, and continue to provide access to these services using the remaining devices.
Ryan, were
that
you able
connected
to
the load
re-upload
balancer.
your report?
For a little
Almost every company now uses.
for a lot of savings.
Here's a common
Yeah, almost
design
every
for a load
company now
balancer
uses
where
some sort
users
of
on the internet
IT
would be
professional
accessing a
to
service at a
You can
to
location.
do
print the
something within
PDF
the
and
company.
upload it.
Perspective, they're accessing a single server, but they're really accessing a load balancer that is distributing that load.
What would you like me to share with you? The course or
Okay, awesome. Thanks.
These load balancers can also
the course or the
optimize the
certifications?
communication. For example, it may perform
Which one are you
TCP
asking to be
offloading
shared with
so
you?
that the communication to all of these servers on the inside of the network are occurring as quickly as possible. These load balancers can also act as an SSL offload, which means that they will provide the encryption and decryption capabilities instead of having the servers themselves manage that process. Data might also be cached on the load balancer, so requests made to the
The
load
courses,
balancer can be
certainly.
answered immediately instead of going all the way down to the server to provide that data. And load balancers are also very good at prioritizing different types of traffic over others. There might be certain web pages that have higher access than others, and you can commonly perform that prioritization using quality of service or QoS. Load balancers can also provide application-centric load balancing, where certain pages may be located on certain servers, and all of the requests to those pages would go exclusively to those individual servers. Many organizations have security.
So I will
that
type
allow
these
individual users
certifications
to
in the
communicate with a server or service that's on the internet.
in the
One of
chat,
the
so
ways
you
that
can see it from
organization
there.
can manage these connections is by putting a device in the middle of this conversation called a proxy. This proxy is responsible for taking the user's request, performing that request on their behalf, receiving the answer to that request, verifying that the answer doesn't contain some type of malicious software or malicious code, and then providing that answer to the end user. That is the purpose of a proxy, to sit in the middle of the communication and make that communication on the user's behalf. Since the proxy is sitting in the middle of the conversation, it's a perfect place to do caching. So the user can make a request to a web server. If that request has already been cached by the proxy server, the answer can go right back to the user without having to access the internet. We might also provide access control from the proxy server so that we can request a username and password from the user in order to gain access to the internet. From that point, we might want to filter URLs or perform some type of content.
Just one moment, I'll give you the certifications and also 2 websites that you can go and do the courses. Also, the Cisco website also give you free courses that you don't have to pay for all of them.
There are also transparent proxies that will work invisibly without making any changes to the operating system or the applications in use. It's very common to store documents and other files on centralized storage facilities inside of our data centers. One type of storage is referred to as a network attached storage, or NAS. We often refer to this network attached storage as providing file level access. That means that if we wanted to gain access to information within a file, we need to pull the entire file across the network into the memory of our system. And when we're writing information or changing information in that file, we will need to write the entire file back to the NAS. A more efficient way of communication might be through the use of a storage area network, or a SAN. This is very similar to reading and writing information from a local storage drive, where instead of copying the entire file to be able to change just a bit of information within it, we have block level access, which means that we can change just the blocks that have been modified. And when you have very large files, this can be a very efficient way to modify just a little bit of information within that very large document. Whether you're using a NAS or a SAN, you're probably transferring a lot of files to these systems. And for that reason, we want to be sure that we're using the most efficient method of communication. It's very common, for example, to put the NAS or the SAN on its own isolated network, and it's commonly a network that has very high bandwidths. If you're in your office and you look at the ceiling, you might see a device like this. This is an access point. This device allows us to communicate wirelessly from our device to the rest of the network. This is not the wireless router that you might be using at home, which is a router and a wireless access point and a switch in the same device. When you're in larger enterprise environments, you're usually using a device that is purpose-built for a single function, and having an access point means that we're using this for wireless communication and wireless communication only. On the other side of this wireless access point is very commonly an Ethernet connection. So this is bridging communication between the wireless network and the wired Ethernet network. That's why we refer to access points as an OSI layer 2 device, or a data link layer device, because it's making that translation between the 802.11 wireless network.
So those are some of the courses that you see that I typed in the chat. Those are some of the courses that I'm currently doing. And the CompTIA and Cisco Network Academy, these are two places that you can go to get those done. They give you all the information there. They also give you the free practice test so you can practice basically exactly what you're going to be doing.
You walk out the door with your settlement check. You just need to get better. Let us worry about all the other problems that come up.
In most businesses of any size, you probably have more than one access point. That's because you probably have a very large building or a series of buildings, and you need to be sure that everyone is able to access that wireless network wherever they happen to be inside of these buildings. But this means that we have to manage many different wireless access points wherever they might be in our local network or in a remote site network. And we might need to manage security settings, access policies, and other configuration parameters within that access point. We also have users that may be very mobile and moving between different parts of the building or moving from one building to the other, and we need to make sure that they can seamlessly roam from one access point to the other so that they are always connected to the network. Instead of connecting to each individual access point to make these configuration changes or manage this process, we can have a centralized management tool that allows us to manage all of our access points from one central place. This is a wireless LAN controller, and it gives us that single pane of glass so that we can manage the entire infrastructure while we're sitting in one chair. From this single device, we can deploy new access points with a full configuration. We might want to set up performance or security monitoring and be alerted if we happen to see anything across any of our access points. We can also take any changes that we need to make and deploy those automatically to all of our access points with one click of the mouse. This also allows us very commonly to create reports on how much our access points are being used and be able to understand if we need to update or change any of our access point locations. These are often proprietary systems, so if we have an access point from one particular manufacturer, then we're also using the wireless LAN controller that is also from that same manufacturer. If you were to somehow get inside of the networking cable and see what was going back and forth over that connection, you would see there was a lot of different activity going on across many different systems. All of these are designed to focus on specific functions. For example, we may need to get a piece of data from our network to a network that is on another part of the world. Or we might need to access a system that is already located somewhere else and provide technical support or be able to share a screen. There's also a need to have traffic management on our network so that certain applications have a higher priority than other applications. And lastly, we need to be sure that all of our systems are up and available, and it may take specialized protocols to make sure that that occurs every step along the way. One way to speed up the process of getting access to data is through the use of a CDN. This is a content delivery network. And as the name implies, it is designed to provide a way to get data very efficiently from one central point to an end user. These are often set up in geographical areas. So there might be a CDN server in North America, South America, Africa, Asia, other parts of the world, and you're able to cache information at each one of these points. It takes time to get data sent from one part of the world to the other, so if you can have all of your North America users access the North American CDN, it's much faster than having them all go out to a centralized server that might be located in Europe. So if you're watching this video on YouTube or on the Professor Messer website, you're using a CDN right now. It's a way for very small or very large sites to be able to distribute their data to users all over the world and make sure that that data is as accessible and efficient as possible.
CompTIA is the IT painkiller. Remote monitoring and management, remote access, help desk and ticketing, smart automations, patching, software deployment.
All right, if you haven't taken a break, go ahead and take one.
Is that it does all this
See you in
while still
10
being
minutes.
used. It's magical. Just this clean, intuitive UI where everything is where it's supposed to be and does what it's meant to do. Sorry, I get it.
For those of you that work outside of your corporate facility or perhaps do a lot of work from home, then you're probably already familiar with a virtual private network or a VPN. This allows you to connect to a remote network while sending all of this data encrypted across the network. It's a very secure way to transfer data even across networks that would be inherently insecure, such as the public internet. VPNs often use a device called a concentrator or a head-end device to be the central connection point for all of the users who are accessing that VPN. This is often a purpose-built appliance that's designed to do high-speed encryption and decryption of network data in real time so that you can have many people being able to send secure data across the network, decrypt all of that data, send it to the inside of the network, and then reverse that process to get the response back to the user. This can be a standalone device, but very commonly we integrate this VPN concentrator function within a next generation firewall itself. Because of the encryption and decryption process required to perform this VPN concentration, we usually will use a purpose-built appliance or piece of hardware to be able to do this. That provides very high throughput and can support hundreds or even thousands of users simultaneously. But if you have a smaller network, you may not need a purpose-built appliance, and there are many VPN concentrators that will run as software on an existing operating system. You may have to install a specialized piece of software to be able to use a manufacturer's VPN, although there is VPN software that does ship with Windows, Mac OS, and Linux operating systems so that you can connect to many different kinds of VPNs using that generic software. Not all applications are designed to run simultaneously on a network, and certainly some applications may have a higher priority to your organization than other applications. For example, there might be a real-time audio or video stream that has a higher priority than a file transfer. Because of these requirements, it's very common for network administrators to provide some type of prioritization to these applications. This is often done through a quality of service or QoS configuration. You might also refer to this as traffic shaping or packet shaping. This allows the administrator to control what type of applications can flow through their network, usually based on bandwidth usage or particular data rates. This might allow your real-time applications to have full control or access to the network and put a lower priority on other applications that may simply be transferring files. To control this quality of service, you may need to make configuration changes inside of a firewall, a router, or a switch. These devices might have a pre-built list of applications and might also allow you to add your own applications to the list. And at that point, you can decide what priority the applications might have relative to everything else that's running on the network. One of the challenges we often run into with technology is that it's very good at performing a task. And often it can perform these tasks over and over and over again without any type of human intervention. Unfortunately, this could also put a device into a state where it's performing the task over and over and over again and never finds a way to complete or end that particular task. For that reason, we've often built in different functions with our protocols so that we can recognize when a task may be going on too long and simply remove that task from the network. One common way to provide this identification is through the use of a time to live, or TTL. A time to live is effectively some type of timer. This timer may be based on the time of day, or it may be based on the number of iterations that a particular task completes. Once that timer hits 0, we can then have that task stop what it's doing, or we can drop that task from the network. There are many different cases for a time to live. One is a packet that is constantly looping between different routers. We might want to have that packet automatically dropped if that loop occurs a certain number of times. Another good example of a time to live might be to clear a cache, where we might access a website, have that website stored in a cache, and then that cache is only available for the next 60 seconds or number of minutes. When that timer hits 0, the cache is cleared, and the next time that website is accessed, you would have to go all the way out to the site to be able to bring that information back, at which point that is placed in the cache and another timer starts. Another example of using a time to live to stop traffic that is looping around your network is through the use of a routing loop. This is a really good example of where you might have router A thinks the next hop is router B, and router B thinks the next hop is router A. And what you'll find is that the packet goes back and forth between those routers over and over and over again. If you were going to perform a trace route, you would see this loop in the trace route itself, where the route goes to 10.1.10.1, then it goes to 10.2.10.2, then back to 10.1.10.1, then back to 10.2.10.2, and so on. And this will continue all the way through until it reaches a time to live.
Purina conducts over 100,000 quality checks every day.
This is something that does occur occasionally because you might have many different routers, and those routers have many different routes. So it's very easy to make one single IP address mistake in a static route and create this routing loop on your network. For routing loops, we use a TTL field inside of the IP packet itself. This allows us to identify and stop a loop automatically if one occurs. In this example, we have router 1, and router 1's next hop is router 2. We've configured router 2 with a next hop of router 1, which means that this packet is going to go back and forth between these routers until something stops that loop from occurring. Fortunately, we've built functions within IP, or the Internet Protocol, to look for this loop to occur and stop it if it finds that it's occurring over and over again. In IP, the time to live is referring to the number of hops that a packet will go through a router. Each time a router processes a packet, it decreases the time to live by 1. And when that value gets down to 0, it discards the packet, effectively ending the loop. The default time to live for Mac OS and Linux is usually 64 hops, and the default time to live for Windows is 128 hops. Since the router is decreasing the time to live by 1 each time the packet goes through, it's watching that number decrease every time it goes through a looped connection. And when the time to live gets to 0, the router drops that particular packet. If we were to look at the frame of IP, you can see there's version numbers, header length, type of service, total length, and other fields within the IPv4 header. The one we're interested in is the one called time to live, and that's the one that the router will use to determine if it's gotten down to 0 and if it should discard this packet from the network. Here's a very simple protocol decode of an IP header. You can see this is frame 1 we have the Ethernet information with the MAC addresses for the source MAC address and the destination MAC address, and this is an IP version 4 header. You can see the source IP address and the destination IP address in the header itself. If we were to break this header open and look at those individual fields that we mentioned from that previous slide, you can see there is a differentiated services field, a total length field, an identification field, and right here is a time to live field. The time to live for this particular packet is 58 hops. So this packet would need to go through 58 more routers until this got down to 0, at which point it would be removed from the network. In most cases, our total number of hops between us and the destination that we're trying to visit somewhere on the internet is usually around 12 to 16 hops, sometimes more and sometimes less. But that's a relatively small number when you consider that the total default time to live on macOS or Linux is 64 hops, and the default on Windows is 128 hops. That gives us plenty of room to be able to get data from one side of the internet to the other and not have that information accidentally dropped by a router. Depending on the protocol you're using, time to live may have a different definition. With routers, time to live is associated with the number of hops, but in DNS or the domain name system, the time to live is associated with the total number of seconds. Let's take a scenario where we're performing a DNS lookup, and you can do this yourself by using NSLookup or dig, and you can resolve or look for the device www.professormesser.com, and your DNS server will return some type of IP address associated with the Professor Messer web server. Inside of that DNS resolution is information about time to live. This tells us how long we should cache this local entry on our system. So if we want to cache it for a certain number of seconds. How many seconds? Well, we're going to cache it for the time to live seconds. The time to live is included with the configuration on a DNS server, and this is the output from the command dig www.professormesser.com. You can see that the answer section, where the DNS server is providing us information, says that the server www.professormesser.com has a time to live of 300. This is an internet address. The A is for address. And then we have 3 different IP addresses associated with my web server. This 300 value is the one telling our local machine, keep this IP address in your cache for 300 seconds. If you do the math, that is 5 minutes. Once that 5 minutes has elapsed, our local cache removes that particular resolution. And if you want to know the IP address...
All right, welcome back from break. If you need something, please let me know. I know you're getting your study time in and getting those last pieces of requirements in. So
this allows me, as the administrator of my web server, to be able to change the IP address in my DNS configuration, and I can feel relatively secure that most people will have an updated version of that IP address within 5 minutes. We use time to live for many other protocols as well, so make sure you look at the documentation for that protocol to understand exactly how we're measuring time to live for that particular protocol.
Auto insurance all seems the same until it's time to use it. With USAA, it's easy to file claims, schedule.
Cloud computing has undeniably changed the way we approach technology. With one click of a button, we can deploy an application and multiple services, all seemingly with unlimited resources. We're able to scale up and scale down these applications as we need, providing elasticity, especially in times when we have large demand, and then scale it back down when that demand goes away. We also have applications that we can now scale up or scale down and access those applications from anywhere in the world. Cloud computing also uses multi-tenancy, where many different customers are using the same cloud infrastructure. This allows for efficiency in the use of technology and efficiency in how much it costs to use this technology. Not only do we have virtual servers that can live in that cloud computing infrastructure, we can also have virtual networks. Let's take the scenario where we might have 100 individual servers that are running in our data center. That's a relatively large farm of servers. We've designed this infrastructure to have redundancy in the network. There are multiple servers, we've got load balancers and multiple firewalls, and we've designed it for uptime and availability. But now let's take this entire physical infrastructure and let's move this infrastructure to the cloud. We're going to migrate 100 physical servers to effectively one very large physical server. Inside that one very large physical server, we will run 100 virtual servers inside of it. Now that we've taken these 100 physical servers and migrated them to a cloud infrastructure, what do we do with our networking infrastructure? Not surprisingly, we will virtualize this network infrastructure as well. This was referred to as Network Function Virtualization, or NFV, where we can replace our routers and our switches and our other networking devices with virtual versions of those networking devices that are running in this virtualized environment. Although our firewall and our switches and our routers are no longer physical, they still have the same functionality. We can see those devices, our network interfaces, and everything about the network configuration all from our hypervisor. So we have the same functionality, it's just now in a virtual appliance. Just as we're able to push a button and deploy a new server, we can push a button and deploy a new firewall or a new switch or make a router configuration all within this virtualized world. This gives us a lot of flexibility for deploying applications, designing the network connectivity for those applications, and connecting our different cloud infrastructures wherever they might be in the world. A common application instance inside of a cloud infrastructure might include a web server, a database server. There could be load balancers, virtual switches and routers, and virtual firewalls. All of these will run inside of a virtual private cloud, or a VPC. It's very common, especially in larger environments, that you would have separate VPCs for different application instances or different parts of the company. This allows you to keep all of these systems separated, but still allow you to manage all of them as individual virtual appliances. Although these VPCs may be different application instances, we might still want to have devices within those separate VPCs be able to communicate with each other. To provide that communication, we need a device in the middle called a transit gateway to be able to connect all of these VPCs together. You can think of this transit gateway as a cloud router that allows us to connect and allow communication between all of our different VPCs. If you need connectivity to these VPCs from the outside, you may need to add additional security in the form of a VPN connection. This allows someone who may be at a remote site to be able to bring up a VPN tunnel, connect to the transit gateway, and effectively have communication to all of your different VPCs. It's very common to use a VPN at a remote site or from a user's workstation to be able to gain access to these private VPCs. But there may be times when you want to make your application instances available to anyone on the internet. In that scenario, you might want to use a VPC gateway, or what we refer to as an internet gateway, so that users anywhere in the world will have access to your applications. We might also want to have these devices in each of our VPCs communicate outbound over the internet to other resources. We would use a VPC NAT gateway to provide this communication, and the NAT stands for Network Address Translation. Our VPCs and the private networks that we're running inside of those VPCs can translate to a public IP address to be able to communicate out over the internet. This includes security rules so that your VPCs can connect outbound to internet resources, but you may not necessarily allow inbound access from external devices. And it's not uncommon for many organizations to use multiple cloud providers, but still require connectivity between those cloud providers. We can provide that connectivity through the use of a VPC endpoint, where we create a direct connection from a VPC on one cloud provider to a VPC.
Grammarly now uses AI to help you write, not just revise. Type a prompt and generate a persuasive mistake
on another cloud provider. Here's an example that has a number of different VPCs. We've got a virtual private cloud with a public subnet for public applications that people can access from anywhere on the internet. We also have a private subnet on the same cloud provider where we have a private virtual machine. Well, if we have a different storage network, which certainly could be at a different cloud provider,
That cloud storage can easily connect to the public subnet over the existing internet and using a VPC internet gateway. But our private subnet is not accessible from the internet, so we need to add a VPC endpoint that will allow our cloud storage to communicate directly to what is a private subnet and virtual machine. Many cloud providers will include additional security that you can layer on top of your VPCs. Security groups and lists are effectively a firewall that's created for your cloud-based services. This allows you to control what traffic can go outbound and inbound to your VPCs. Most of these are based around a series of port numbers and protocols. So you can define a TCP or UDP port number and add that to your inbound or outbound rules in your security groups. You can also add layer 3 addresses to this, so you can add IP addresses that are individual addresses, maybe an entire block of addresses using CIDR block notation, or specify IPv4 or IPv6 ranges directly within your security groups. This is very similar to configuring a traditional firewall, which operates looking at TCP or UDP port numbers. In this example, the inbound rules have a number of predefined rules, but you can customize these as well with your own port numbers specific to your application. In your cloud provider's front end, you would include in your network security list the list of rules that you would like to assign. For example, I have a rule that is inbound using TCP port 443, and any IP address is allowed to communicate inbound with that rule. I have another rule that's an inbound rule for TCP port 22, and it's the same broad range of any IP address. Once you define your network security list, it will be applied to all of your virtual private clouds. You can see that I have a virtual cloud network for subnet X, subnet Y, and subnet Z. These very broad network security lists will automatically be assigned to each one of those individual networks. One of the challenges with these network security lists is that they don't provide a lot of granularity. When you configure a network security list, it's automatically assigned to all of your virtual cloud networks, even if you don't need that particular rule in that cloud network, and even if you need additional rules for one of the individual cloud networks. Fortunately, there are ways to add additional granularity using a network security group. With a network security group, I can assign rules to individual virtual network interface cards, or VNICs. So you can see I have similar security rules that I've defined as a network security group. I have network security group A, which is inbound TCP to port 443, and I have a network security group B, which is also an inbound rule to TCP port 22. I've identified these as the network security group A with the green shield and the network security group B with the blue shield. And you can see that I can assign those network security groups to individual network interface cards that may be inside of a virtual cloud network. This one is on a single subnet where I've defined different rules for different interface cards within the same virtual cloud network subnet. You can see by using these network security groups that we do have additional granularity that we can bring down to the individual interfaces. But this also increases the amount of administration required to manage all of these different lists. If you find that you need additional security above this, you might want to look into a virtual firewall or other virtualized platform to include additional security to your application instances.
Cascade Platinum Plus has the grease-fighting power of Dawn to remove tough, stuck-on foods. Cascade Platinum Plus.
Progressive's Up-Payment program provides down payment assistance for first-generation home buyers.
When you're deploying a cloud-based application, you also need to consider who will be accessing that application and from where. If you're creating an application that anyone on the internet would need to access, then you would probably want to include it in a public cloud so that everyone can gain access. But if you're building out a cloud-based application that is for internal use only, you may want to deploy this to your own virtualized local data center where you have a private cloud. In many organizations, we often use both of these, and we need a hybrid configuration of both public and private clouds for all of these applications. One type of cloud model is software as a service, or SaaS. This is commonly associated with software that is on demand. You have a login screen on your browser, you log in, and now you have access to the application. Someone else has written the application, someone else manages the application, your data is stored somewhere within that application, and you don't have to do anything else to be able to use that particular app. You don't have a local installation of software, you don't manage or upgrade any of the software itself. Instead, you simply log in and use the app. This allows for centralized management of the application and the data that you're putting into the application, which means everything is being stored on a third-party cloud platform. This is a complete application offering, and you don't have to do any type of development work to be able to use that app. A good example of software as a service would be an app like Google Mail or Office 365, where you simply log in and use the app. There may be times when you would like to build your own application and deploy and manage your own data, and all you really need are the computing resources to be able to run that application. In that model, you want to use Infrastructure as a Service, or IaaS. Sometimes you'll see this referred to as Hardware as a Service, or HaaS, because you're effectively using hardware in the cloud and then using your own software on top of that. This means that you would be responsible for installing your software and managing all of the data associated with that software. If the software needs to be upgraded, you would be the one to upgrade it on your Infrastructure as a Service model. The application that you're using and the data that you're putting into that application is still in the cloud, but you have much more control over the access and security of that data when you're using Infrastructure as a Service. A good example of Infrastructure as a Service is with web service providers, where you can buy time on a particular web server and they make that server available to everyone on the internet. A middle ground between software as a service and infrastructure as a service is Platform as a Service, or PaaS. This is still in the cloud, but you're the one who manages all of the development efforts to customize the application to your specifications. The cloud provider gives you all of the tools necessary to build this particular app. You can think of this as a series of building blocks provided by the Platform as a Service infrastructure, and then you build out those blocks to create your own application. The underlying engine that runs the application is the responsibility of the Platform as a Service provider, and your responsibility is to build and maintain the apps that are running in Platform as a Service. A good example of a Platform as a Service infrastructure would be something like Salesforce.com, where they give you all of the tools necessary to create a customized application running on the Salesforce.com platform. Here's an example of a cloud responsibility matrix that you might find with any cloud service provider. In this chart, I've separated out software as a service, platform as a service, infrastructure as a service, and then an on-prem device that you would manage yourself. Obviously, with on-prem, everything from the data to the applications to the physical data center are all the responsibility of the customer. But with infrastructure as a service, you have the physical data center, the physical network, and the physical host, all provided by the cloud provider, and then you handle all of the other pieces of that particular application. With Platform as a Service, you can see that network controls, applications, and the identity and directory infrastructure may be shared between the customer and the cloud provider, but you'd still be responsible for the accounts, devices, and the information and data. With software as a service, much more of these are provided by the provider themselves. For example, everything associated with the applications is clearly in the responsibility of the provider. Everything above that would still be the responsibility of the customer. So depending on the type of infrastructure you want and the type of responsibility that you're willing to take on, you'll need to pick the right cloud model for your application deployment. In this course, there will be a lot of conversations about TCP/IP, moving packets across the network, and very often we lose track of exactly what that means. So I thought it would be good if we start with an overview of Internet Protocol and how it operates. The goal, of course, is to get data from one side of the network to another. And there are a number of different processes involved in being able to transfer large amounts of data from one computer to another. In the analogy that we use today, we're going to describe this transfer of data from one device to another as using a moving truck to get data from one house to another. We can also think of the roads that we're using as the network that we've created. This might be a wired Ethernet network, a wireless network, a wide area network technology, or many different types of network connections. But in this explanation, those network connections are referred to as the road that our moving truck will drive on. In this example, this truck is the Internet Protocol. It's the one that is doing the heavy lifting and moving that data across the network. Just as we might pack up items or objects in a room into a box and put that box onto the moving truck, we do effectively the same thing with our application data. We package that information into a virtual moving box, and we put that moving box onto the truck, which in this case would be IP. So now we have a highway, which would be our network. We have a moving truck, which would be the Internet Protocol. We have boxes within that moving truck. We commonly refer to those boxes as the TCP or UDP protocol. And then inside of those boxes is application data that we need to transfer from one device to another. This process of encapsulating data within other protocols, which are then encapsulated within even larger protocols, is a fundamental process when we describe the transfer of data across the network. If we were to visualize the Ethernet frame that we use on our networks, it would look a lot like the one that we have on our screen now. We have a client that is communicating to a server, and information is being sent between those two devices. You'll notice there is an Ethernet payload in the middle of this frame. At the beginning of the frame is an Ethernet header, and at the end of the frame is an Ethernet trailer. If we were to provide a little more detail about what's inside of that Ethernet payload, you would see there would be some IP information, and within the IP header, the rest of the packet has the IP payload. Deconstructing this further, you can see that the IP payload consists of a TCP or UDP header, and inside of that part of the packet is the TCP or UDP payload. So if we were to look at a protocol decode of a single frame on our Ethernet network, we would see an Ethernet header. Inside that Ethernet header would be an IP header. Inside the IP header might be a TCP header, which would hold HTTP or website data. And then finally, at the end of the frame, we would have the Ethernet trailer. You'll notice that inside of that IP header, we had either TCP data or UDP data. So it might be useful to break out those two protocols and describe what the differences might be. Both of these protocols are very similar in their function. They're obviously moving data from one device to another, but the internals of how those protocols work are a bit different between the two, and an application will use the one that makes sense for its particular function. If you recall our video on the OSI model, you'll remember that TCP and UDP operate at OSI layer 4, or the transport layer. It's in this layer that we're able to send many different applications across the network simultaneously between exactly the same devices. We refer to this as multiplexing, and it describes the efficient process of transferring multiple applications simultaneously between multiple devices. Let's first look at TCP, or the Transmission Control Protocol. We refer to TCP as a connection-oriented protocol. That's because there is a formal process to set up the communication between two devices, and when that communication is done, there is a formal process to tear down that particular session. One feature that makes TCP different than UDP is the ability for a station to acknowledge that it has received data. We refer to this as a reliable delivery method. That's because sending data to another device will always result in an acknowledgement that that device has successfully received that data. This means the sending station will always know if information was properly delivered to the destination. This also means that the sending device can recover from any type of errors. If it doesn't receive an acknowledgement, it can assume that that information was not received by the destination device, and it will resend that information to ensure that it is able to receive all of the data. These packets are also numbered, so the receiving device will also be able to request anything that may have been lost along the way without having to resend multiple packets and recreate that data. Having this conversation between these two devices about how well traffic is able to be transferred allows the receiving station to configure flow control. This describes the process of the receiving station telling the sending device to either send data slower or speed up the transmission. UDP, or the User Datagram Protocol, is a much more bare-bones protocol. There's no formal process to set up a session between two devices and no formal process then to tear down that session. We refer to this as a connectionless communication because there's no setup or warning that information may be inbound to a particular device. This means that we can send packet after packet of UDP data from one device to another, and no UDP acknowledgement is ever sent back to the originating device. We refer to this type of communication as unreliable, not because there is a higher chance of having problems communicating. In fact, UDP and TCP are able to communicate in exactly the same way with exactly the same probability of getting that information sent across the network. The difference is that we don't receive any acknowledgments when using UDP, so we can't guarantee that that information has truly been delivered. And since there's no acknowledgement and no notification that anything has been delivered, there's no way to perform any type of error recovery or be able to retransmit portions of the data which may have not been received. And because there's no ongoing communication back and forth between these two devices using UDP, there's no way to configure any type of flow control. The receiving station can't reach out and tell the sending station to speed up or slow down because nothing is ever sent back to the originating station.
It's the final game, folks. This one wins the series. Struck out with the cheap seats. Important things aren't worth compromising. At Farmers, we offer both quality insurance and great savings. Here, take mine. We are Farmers. Bum, 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 bum.
When your kid is hurting and there's nothing you can do about it, that's the worst feeling in the world.
Now that we've loaded our boxes of data into our IP truck, we need to tell the truck driver where to take this information. And in a moving truck, we do this by giving the truck driver the destination address for the truck. In the world of IP, we give it a destination IP address. But of course, in a house, we have many different rooms that we might deliver these boxes to. Some boxes might be for the bedroom, others might be for the kitchen or bathroom. And when we bring the box into the house, we can take that box directly to the appropriate room. IP works in a similar way, where each box of data is provided a room name. And in the world of IP, it's provided via a TCP or UDP port number. Instead of having bedroom, living room, kitchen, or bath, there will be a number associated with that data, such as port 80, port 443, port 123, or port 25. When those TCP or UDP boxes arrive at the house, we simply look at the TCP or UDP port number and deliver that box to the appropriate application running on that server. If you were to look at a protocol decode of IPv4 traffic being sent over the network, you would see a set of IPv4 sockets for the server and for the client. This socket is a combination of data that consists of an IP address, a protocol, which would be TCP or UDP, and then there would be an application port number. For the server side, there would be a server application port number, and on the client side, there's a client port number. Once both sides of the conversation know what the IP address is, they know the protocol, and they know the port numbers of both the server and the client, we're able to send information properly between both devices to the appropriate application. If you were to look at well-known applications that are using TCP or UDP, you'll notice that many of those port numbers are from 0 through 1023. We refer to these as non-ephemeral ports, which means they are permanent port numbers. If we need to communicate to a web server, we're almost always going to use port 80 and port 443. Those are very common and permanent port numbers that you would find on almost any web server. On the client side, we tend to use port numbers on a temporary basis. We refer to those as ephemeral ports. Those are ports that are commonly associated with 1024 through 65,535. Although it's very common to find applications using non-ephemeral ports and the clients using ephemeral ports, the reality is any device can use any port number that it would like to. And although we commonly associate servers with non-ephemeral ports and clients with ephemeral ports, the reality is you can find application servers using port numbers within the ephemeral port range. So you can see this is not a hard and fast rule, but instead broadly describes the way that we use these port numbers on our network. Anytime you see a TCP or UDP port, it can be a number between 0 and 65,535. That is a lot of room to be able to use different port numbers for different applications. Most servers, as we mentioned, will use non-ephemeral or non-temporary port numbers, but that's not always the case, and you could see applications using port numbers that are in the ephemeral port range. Remember that changing port numbers is simply a way to designate what room inside of the house will be receiving that particular data. It's used for communication. This is not a security mechanism. You'll still need a firewall to decide whether traffic is truly allowed or disallowed through the network, and simply changing a port number doesn't increase or decrease any type of network security. If you're connecting to a web server, your browser automatically knows that it should be looking for port 80 or port 443 and will use those ports by default. If you change the port numbers of the server, your browser will no longer know how to connect to that web server. That's because we expect web servers to always use port 80 or always use port 443. These are well-known port numbers, and if you change those port numbers, you'll have to make sure that all of the clients use the new port number instead of what normally would be well-known. Also keep in mind that TCP port numbers are different than UDP port numbers. Although both of them can be between 0 and 65,535, TCP port 80 is a different port number than UDP port 80, and you could theoretically use two different applications with both of those protocols at the same time. Here's how this might be practically configured on our network. In this example, we have a server, its IP address is 10.0.0.2, and we have a client at 10.0.0.1. These two devices are communicating across the network using three different applications. The server has a web server at TCP port 80, a voice over IP server at UDP port 5004, and it's also providing email services over TCP port 143. This means the client can communicate to the server with all three of those applications simultaneously because they all have different TCP and UDP port numbers. If we were to then look at the IP data that was being sent on a single communication, you can see that this IP address of 10.0.0.1, our client, is sending information to this 10.0.0.2 address. You'll also notice that the client is using a temporary port number for this session. In this case, the randomized temporary port number is port 3000. And this device is communicating to the web server, so it's using the well-known port number of port 80. And you can also see there is HTTP data contained within this packet as well. This data is received by the server, and when the server needs to send information back to the client, it simply reverses the TCP source port and destination port and the IP source and destination to be able to send that information back to where the original request was sent. This same process occurs if you're using voice over IP data. In this case, the client is using a source port of 7100, and the UDP destination port would be 5004, which would be the voice over IP service on that server. And for email data, the source port that's being used is a random number of 4407, and the destination port is the well-known port for email, port 143. So every device on the network that is communicating via IP is
Leah's
using
back.
this fundamental process
What'd
to
you get?
transfer data.
739.
To scale up into a worldwide internet and be able to send data between two devices.
Congratulations. You are A+ certified. Look at you.
Coach here to tell you about an all-star bundle. It's Disney Plus, Hulu, and ESPN.
You right, I do owe you lunch. You right.
It's as easy as
Yep.
catching a football. It's as easy as catching a football.
When I got you, and I got you.
Oh yeah!
Good job.
Typically, you say ready before you throw it.
Disney Plus, Hulu, and all ESPN. 3 All-Stars, 1 incredible offer.
If you have any techniques you want to share with the class with the PVQs, feel free.
The PVQs, there was a help desk one where like you had to like chat with a customer and like just it was like a multiple choice kind of thing where they give you a list of responses, so you just choose one. And then what was the other one? Oh, there were two that were exactly like the ones you showed us. Like with choosing like IP address for like the network. I'm trying to think. I had 4 of them, and I had 3 last time, so that was interesting.
What IP address schemes did you pick for the Xbox, home router, Wi-Fi?
I really don't know if I got those right, but I chose.
TCP port 20 is commonly associated with the file transfer process itself, and port 21 is commonly.
It was the one where we had to put like a router, like choose which one.
Has an authentication method, so you
I chose the.
And when you're transferring information,
what's the IP address? Like what? I don't know. I'm gonna type it in the chat real quick.
Directory, add different files, delete, rename, and perform other types of file maintenance. TCP port 22 is commonly associated with SSH.
Is that like a specific kind?
This is a way to communicate to a remote device from a console.
That is the public.
So you have this text-based
I chose that one for like
manage this device over this text-based
public side of the router.
Yes.
For the house.
Characteristic of SSH.
Yes.
Mine was it was a gaming console.
Yeah. So did you choose that public for the house router? Right, for the home?
No, I put the private IP for the PC.
Okay, good. All right.
So I don't know if I got it right or not, but yeah.
They give you partial credit. So 50 is for the external for the house at the demarc point. Then the router will give you an internal address, usually 192.168 something. And then from there you can parse out what ports you want to do what inside the router. So you did good. You had 730 something, so you did something right.
Port 22. And just like our FTP protocol allows us to perform file management of that device, we can also perform the same file management using the secure version of FTP. So you can view the directories, you can make changes to the directory names, you can modify files, delete information, and perform all of the normal file management from the secure FTP application. Both Secure Shell and Secure FTP have that foundation of SSH as the underlying protocol. So not only does Secure Shell allow you that remote terminal communication, you can also have remote file transfer communication, and all of that communication will be encrypted using the SSH protocol over TCP port 22. Before we had encryption over SSH or Secure Shell, we used a non-encrypted form of terminal communication referred to as Telnet. This stands for Telecommunication.
If y'all have any questions, go ahead and chat it up with Leah.
Visually, this looks almost identical to what we use with Secure Shell. The difference, however, is the communication that we're sending between our device and the remote station is all being sent in the clear. There's no encryption that's taking place across the network. This means that someone could potentially capture those packets and view everything that's being sent back and forth over the network, including your login credentials. It's for this reason that you don't commonly see Telnet being used on our network, and instead we'll use SSH to ensure that all of this communication will always be encrypted. Another important application on our network is the use of email. And of course, we need protocols to be able to transfer these emails from one email server to another. To be able to do that, we use SMTP, or the Simple Mail Transfer Protocol. SMTP is commonly associated with server-to-server email transfers using TCP port 25. All of this traffic sent over TCP port 25 is sent in the clear, or in plain text. There's no encryption that's automatically configured when using TCP port 25. That's why many SMTP servers will use TCP port 587, which is SMTP using TLS encryption or the transport layer security. SMTP is also used from client devices that are sending email messages, and it's often sending those to a mail server using this SMTP protocol. For receiving email messages and being able to manage your email inbox, we often use other protocols such as IMAP or POP3. So anytime that you are sending email or you're transferring email between email servers, you're probably using SMTP or the simple mail transfer protocol.
Limu Limo at your service. Here to help you save hundreds by customizing your car insurance with Liberty Mutual. Probably should have gone the other way.
Only pay for what you need.
Liberty, 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 liberty.
We don't often memorize the IP address of devices that we communicate with. Instead, we use the fully qualified domain name, or FQDN. And the way that we translate between the fully qualified domain name and the IP address is we use a DNS server, and that stands for Domain Name System. DNS commonly uses UDP port 53 to be able to perform this name query. So we'll ask a DNS server what the IP address of www.professormesser.com might be, and it will respond back with the IP address that your device can use to communicate to that server. For those small queries, we commonly use UDP port 53, but if there's a large transfer of data from one DNS server to another, we commonly would use TCP port 53. These DNS servers are obviously very critical resources because without them, we wouldn't be able to communicate to servers such as ProfessorMesser.com. This is also a very common protocol to find on the network, and if you take a packet capture, you're almost guaranteed to capture some type of DNS traffic. We've become very accustomed to simply plugging into a network or connecting to a wireless network and automatically being able to communicate across that network. But behind the scenes, there is an automatic IP configuration process using DHCP, or the Dynamic Host Configuration Protocol. This is the protocol that allows us to automatically configure IP address settings for anyone that connects to the network. By default, DHCP uses UDP port 67 and UDP port 68. To be able to use DHCP, we need a DHCP server. At home, we commonly use a DHCP server that's integrated into an existing wireless router, but in an enterprise network, there are often standalone DHCP servers. We usually configure a pool of IP addresses on DHCP, and anyone who connects to the network will be automatically assigned an IP address from this available pool of addresses. There's also a lease time associated with this IP address, so you're only able to use that IP address for a certain amount of time, and if you are still using that address at the end of the leasing period, you can choose to renew that lease with the DHCP server. We can also configure certain devices to always receive the same IP address every time they connect to the network, and we associate that IP address with the MAC address of that device. We configure that in the DHCP server. That's often referred to as a DHCP reservation. All of this communication that occurs across the network for DHCP will almost always use UDP port 67 and UDP port 68. We talked earlier about the FTP, or file transfer protocol, that we use to send files from one device to another. And we described the process of authentication and the many different management functions associated with FTP. But what if you just needed to transfer a small bit of configuration information from one device to another? You don't need to view the name of a directory or change any of the file names. You simply need to transfer a small amount of information very, very quickly. To be able to do that, you might use TFTP, or the Trivial File Transfer Protocol, and by default, it uses UDP port 69. You'll often see TFTP used for very simple file transfers. Usually, this is something that doesn't require any type of authentication or login process, so it may be something like a voice over IP device that has no IP address and no configuration. And when you plug it into the network, it is powered on using power over Ethernet. It uses DHCP to get an IP address, and then it uses TFTP to be able to download the latest configuration file from the server. This is a quick and easy process. It transfers data without any extra overhead, It's able to do that very efficiently and very quickly using UDP port 69. If you're communicating to a web server, you're probably using one of two different port numbers. This is using HTTP or HTTPS. This stands for Hypertext Transfer Protocol, and it's a communication that is commonly associated with browser-based communication. If the information between your browser and the web server is being sent in the clear without any type of encryption, it's commonly using TCP port 80. If you need to perform encryption of that data, and that is probably the default for most websites that you'll visit these days, it is using SSL, that stands for Secure Sockets Layer, or a newer version of SSL referred to as TLS, or Transport Layer Security. If this is encrypted data, then it's probably using TCP port 443, which is sending HTTPS for secure. Another thing you may notice with the devices that are connected to the network is they all tend to have the correct time and date, down to the second level. We're able to do that through an automated process called NTP, or the Network Time Protocol. Every device on the network, operating systems, routers, switches, and any other device, can use NTP to stay synchronized with their clock across all of those different devices. By default, NTP uses UDP port 123. Being able to synchronize these clocks is more than simply a convenience. In fact, it can be a very critical part of synchronizing log files between very diverse devices. This allows us to go back in time and piece together communications, even though that communication occurred on many different devices. This is a process that usually occurs automatically behind the scenes, and many devices will synchronize their clock multiple times during the day using the NTP protocol. You might also be able to configure this process. Maybe you'd like a device to update its clock every hour, or maybe simply updating once a day is sufficient. This is also a very accurate way to keep these clocks in synchronization. And usually we get about a 1 millisecond difference between devices that are all on the same network. This provides a level of granularity that's sufficient for most applications, and it's something that occurs automatically using UDP port 123 and the Network Time Protocol. As a network professional, you'll be responsible for the uptime and availability of routers, switches, firewalls, and many other devices on the network.
Ryan, you still working on the resubmittal?
Devices is through a protocol named SNMP, or the Simple Network Management Protocol. By default, SNMP uses UDP port 161 to query devices and receive information about how that device may be performing. For example, we might have a management station, and we might be querying a device to determine how much traffic has traversed that particular device over a certain amount of time. And then it can provide us with a summary of how much data has been transferred over that time frame. We can then store that data, create graphs, reports, and other information that allows us to manage that device. You might also find that different versions of SNMP may be used on your network. Version 1 of SNMP is the original version. This allows your management station to perform a single query to this device and receive a single response, and all of this is sent over the network in the clear with no encryption. Version 2 of SNMP allowed for bulk transfers, so we can ask for many different variables from this device and receive a large group of data from that device, which simplified the network communication and made it much more efficient. But it didn't provide any type of encryption. All of this information is still being sent across the network in the clear. A more modern version of SNMP is what you may commonly find on your network today, which is version 3. This is a more secure standard for SNMP, which allows message integrity, authentication, and encryption of the SNMP data.
Grammarly's proactive, automatic writing suggestions are great, but sometimes you just want to tell Grammarly how to help. Good news?
One of the things you'll find with this default use of SNMP is the management station is interactively making a query and then receiving a response for that query. So it's up to the management station to initiate that communication. But it would be nice if these devices could identify problems and proactively send that information down to the management station. We can do that by using a feature of SNMP called an SNMP trap. This allows these notifications to be sent directly from these devices using UDP port 162. Many organizations may have hundreds or thousands of devices on their network, and it may be a challenge to be able to keep track of what devices are on the network, what users are connecting to those devices, and how the relationship might be between the user and the device. We're able to maintain a database of all of these devices and all of these users through a protocol named LDAP. LDAP stands for Lightweight Directory Access Protocol, and it commonly uses TCP port 389. LDAP allows us to very easily query these databases and retrieve information that we may have stored. There's also a secure version of LDAP called LDAP Secure. It uses TCP port 636. LDAP uses a hierarchical structure to be able to lay out the network and the devices. This is a graphical view of an LDAP database. It starts with the root of the database, which is an organization. In this case, the organization is Messer Studios. We've also grouped together like devices into organizational units. There is a production OU, a support OU, and an engineering OU. Within those organizational units, there may be common named devices. For example, there may be users such as Jack and Daniel, or there may be a database or storage device named TechDocs. We're able to organize and access these devices through this structure, making it a very common and simplified way of gaining access to this data. Microsoft Windows has some very unique features when it comes to data transfer. Microsoft stores information on the network in a file share. You can also share printers through Microsoft's operating systems, and there is also authentication built into this entire process. To be able to provide all of this functionality, there is a specialized protocol named SMB, or Server Message Block, to be able to share files, share printers, or authenticate to the network. You might also see this referred to as CIFS, or the Common Internet File System. SMB is integrated into Windows itself. You don't need to add additional software. There's no additional FTP or SFTP process. Instead, built into the Windows Explorer or the File Explorer within Microsoft Windows is the SMB functionality that allows us to access file shares, print to remote printers, lock different files on the network, and provide processes for authentication and permissions for all of that data. Early versions of Microsoft Windows used the NetBIOS protocol to be able to facilitate this communication. But most modern versions of Microsoft Windows communicate directly across the network using IP, and TCP port 445 is the one that is usually associated with Server Message Block, or SMB. As a network professional, you'll find that you are constantly referring to logs that are being kept on your routers, your switches, your firewalls, your servers, and almost any other device that's connected to the network. One challenge is being able to consolidate all of these different log files to one single location. And there is a standardized protocol for transferring these log files called syslog. Syslog commonly uses UDP port 514 to be able to transfer this log data across the network. You'll often use syslog in conjunction with a security information and event manager, or a SIEM. This is a consolidation point where you can have all of your log files transferred into one single consolidated database. So if you're using syslog and transferring that over UDP port 514, then you're probably transferring it to a very large drive array or some other device where you can collect that log information over an extended period of time. We store a lot of very diverse information on our databases, but fortunately there's a very common form of storage and retrieval for those databases referred to as a structured query language, or SQL. Some people refer to this as SQL. This SQL database uses a standard language that you can use to be able to query and retrieve information from that database. Microsoft has its own form of SQL database called the Microsoft SQL Server, or MS-SQL. It stands for Microsoft Structured Query Language, and very commonly uses TCP port 1433. There are other types of SQL databases you might find on your network, and they usually use different port numbers. So if you see TCP port 1433, then you're probably using a Microsoft SQL Server. Many of us start on the help desk to be able to provide support for our end users. And one way that we're able to view the remote desktop of those devices is through the use of RDP, or the Remote Desktop Protocol. RDP uses by default TCP port 3389 to be able to view that remote desktop. The Remote Desktop Protocol is commonly associated with a service that's running on a Windows device. But fortunately, there are many clients that can use RDP to connect to those Windows devices, so it's not unusual to find RDP clients for Windows, Mac OS, Linux, iPhone, Android, and many other operating systems. There are many different protocols used for voice over IP. One of the most popular is SIP. This is the Session Initiation Protocol, and it commonly uses TCP port 5060 and TCP port 5061. SIP is commonly used as the control protocol that we use when we pick up the phone, we dial the number, it initiates the phone call, and then when the phone call is over, it disconnects the session. You might also see SIP being used for extensions of voice over IP that provide video conferencing, instant messaging, and even file transfers. All of this takes place using SIP over TCP port 5060 and TCP port 5061.
Dear Friday, we've got power tailgates to power game days. And a trailer backup guy that's the champ of the ramp. Toyota trucks. Toyota. Let's go places.
We are Purina. We believe in keeping pets and people together. That's why we're helping.
There will be many times as a network professional when you'd like to know if a device is on the network and operating. And one protocol that can provide you with that is ICMP. This is the Internet Control Message Protocol. You can think of this as a way to check in with that device, very similar to sending a text message to see if you get a response back from someone. ICMP is another protocol carried by IP, but it doesn't use TCP or UDP. Instead, ICMP is its own protocol. Although ICMP can be used for a number of administrative tasks, it's most commonly associated with a way to send a message to a device to see if it's alive and operating on the network and see if you can get a response back from that device. Whenever you use the ping command to ping an IP address on the network, it's using ICMP to provide that ping functionality. But ICMP can also provide you with information about other things that may be happening on the network. For example, if you're trying to access a network that is not accessible from your location, ICMP will give you a message that that network is not reachable. Or ICMP can tell you that the time to live that's inside of data that you've sent has expired and it's received an ICMP time exceeded message from that device. Another common protocol on our network is GRE, or the Generic Routing Encapsulation Protocol. If you're creating a tunnel between two endpoints, this is commonly done with VPNs, for example, you're creating this tunnel using GRE. This allows us to encapsulate information within an IP packet, send it across this GRE tunnel, and decapsulate it on the other side. This does not, however, provide encryption of this data. We'll need to provide additional VPN protocols to encrypt the data that we are encapsulating in a GRE tunnel. These VPN protocols are referred to as virtual private network protocols, and it's very common to use these VPN protocols to encrypt or protect any data being sent across one of those tunnels. It's often common to use a purpose-built appliance to provide this encryption and decryption process at the central point. We refer to this as a VPN concentrator. Sometimes this is a standalone unit. It's very often integrated into an existing firewall that's connected to the network. These concentrators are often hardware devices with specialized encryption hardware built into the device to add efficiency and throughput. But if you have a limited number of users, it's also possible to use your VPN concentrator as software in an operating system. This is a common site-to-site VPN configuration where a corporate network may be connected to a remote site over a public network such as the internet. We'll have VPN concentrators, which are usually firewalls or routers. Those are connecting these two sites together over the internet, But all of this traffic that's being sent across that public internet is being encrypted using this VPN technology. One of the popular protocols used to provide that level of encryption over those tunnels is IPsec. This stands for Internet Protocol Security, and it's one of the most popular ways to encrypt data being sent across these VPNs. Not only does IPsec provide encryption for confidentiality, it can also provide digital signatures of every packet, which includes integrity and anti-replay functionality. This is also a very common protocol, and it can be used across many different manufacturers' devices. For example, you might have a firewall from one manufacturer on one side of a VPN tunnel, and a firewall from a completely different manufacturer on the other side of the VPN tunnel. Because IPsec is such a standard protocol, those two firewalls can easily connect to each other and transfer information over that IPsec tunnel. When you're using IPsec, there are commonly two primary protocols that are in use. One is the authentication header, or AH, and the other is the encapsulation security payload, or
All right, everybody, it is
in
lunchtime.
order for IPsec
I will see you when you get back
across the network,
in an
we
hour.
first need to create this
So don't forget to clock
tunnel.
out
And
of
we do this by
class
performing
and
a series
clock
of
in.
steps prior to sending
Kevin says
data
getting ready
to
to
this
head for the test. So do me a favor, Kevin.
exchange, or Internet key
Good luck
exchange
and pass
allows
it.
both sides of the conversation to agree on the
All
encryption
right,
and
see y'all in an
decryption
hour.
keys that will be used for the duration of that VPN tunnel. We refer to this agreement as a security association, or an SA. There are two phases to this key exchange process. The first phase commonly uses Diffie-Hellman to create a shared secret key for both sides of the conversation. This usually operates using UDP port 500, and we refer to this as ISACAMP. This is the Internet Security Association and Key Management Protocol. In phase 2, we coordinate which ciphers should be used for the encryption and the key sizes that would be appropriate, and it negotiates both the inbound and outbound security association to be used for this IPsec tunnel. So visually with phase 1, we're building the ISACAMP tunnel over UDP port 500. In phase 2, we're including the encrypted data over the encapsulation security payload, or ESP tunnel. This gives us the foundation we need to be able to send this encrypted data over the IPsec tunnel. If you're building your own IPsec tunnel, you may be asked whether you'd like to use transport mode or tunnel mode. Both of these work differently and will protect data in different ways. Let's take the original packet, which includes an IP header and some data within that IP packet. We would like to send that over an IPsec tunnel. If we use transport mode to send this IPsec data, we're going to insert an IPsec header between the IP header and the data. All of that is going to be in the clear. Anything within the data portion of that IP packet will be encrypted, and then the IPsec trailer is put at the end of the packet. Notice that the original IP header is not encrypted when using transport mode. And if someone does capture this data, they'll be able to see the original IP header and be able to understand where this traffic is intended to go, even if they can't see the encrypted data within the packet. A much more secure method of using an IPsec tunnel is tunnel mode. In tunnel mode, the original IP header data is all encrypted, and even if you capture this data, you'll never know what the original destination is for this data. Tunnel mode adds a new IP header, which includes the destination of the IPsec concentrator, and includes the same IPsec headers and IPsec trailers that we saw in transport mode. It's probably not too surprising that most implementations of IPsec are going to use the tunnel mode to ensure the highest level of encryption of your original data. Earlier, we mentioned the two protocols that you commonly see associated with IPsec. One of those protocols is the authentication header, or AH. AH is used to validate the information that you're receiving over an IPsec tunnel. And if you're only using authentication header mode, you're sending all of this information over the network in the clear, but you're including some additional hashing to ensure the integrity of this data. However, in most cases, we want to be able to encrypt the data that we're sending over the IPsec tunnel, and for that reason, we'll use Encapsulation Security Payload, or ESP. This protocol is going to encrypt that original data and encrypt the trailer that we're associating with ESP, and then put around this packet a new IP header an ESP header, and an integrity check value at the end of the packet. This is going to encrypt all of your original data, but also provide the authentication that you need to ensure that the data is received properly on the other side.
Bounty is 2 times more absorbent, so you can get more done with one. The quicker picker-upper.
A unicast is one of the more popular ways of sending information across the network. It is when one station sends information directly to another station. This is a one-to-one relationship, and nothing within that conversation is ever sent to anyone else on the network. If you need 2 devices to be able to send information to each other, and no other device on the network will be involved with that conversation, then you're probably using a unicast. So anytime you're connecting to a website, you're transferring files, or you're checking your email, it's probably all taking place with a unicast communication. This one-to-one relationship is also one of the disadvantages of unicast, especially if you need to send information to many people simultaneously. With unicast, you would have to build separate one-to-one communications with all of those individuals, and you would have to send separate data for each individual device. But for single communication between you and another device, whether you're using IPv4 or IPv6, you're probably going to use unicast. To be able to efficiently send data to multiple devices at the same time, then you'll probably want to use multicast. Unicast is a one-to-many of many communication, so when you send information out, it is sent to multiple recipients all simultaneously. These recipients are usually subscribing to your multicast feed. So if someone is trying to receive multimedia, they're receiving stock exchange information, or maybe a device is sending out routing updates, you can send those out via multicast addresses. Multicast is relatively specialized, and it requires that equipment understand and recognize how to deal with multicast communication. This is why we don't use multicast when we're sending information across to a different network, or even within a very large network. But we do use multicast quite a bit with IPv4 and IPv6, and in the right environment, it can be a very efficient way to send and receive traffic. Multicast is used where one device needs to send to many of many devices. Anycast is used when one device needs to send to one of many devices. This is where a single destination IP address may be sent to one of many different devices that are on the network, and it's something that you'll commonly find with both IPv4 and IPv6. In this scenario, the devices that are receiving the anycast communication are all configured in very similar ways. This allows the originating device to simply send data to the unicast address, and whatever device is closest is going to receive that traffic. A good use case for anycast would be something like anycast DNS, where a DNS query can be sent out on the network, and the closest data center will be able to respond to that anycast DNS request. And if you want to send a frame to everyone who's on your network, then you'll want to send a broadcast. This is a one-to-all relationship where a single packet is sent out and everyone on the network receives that single packet. Fortunately, the scope of this is limited to your local broadcast domain. So there's no way to send a broadcast frame from your local network and somehow have that frame appear everywhere else on the internet. This is a type of communication that's best fit for something like routing updates or ARP requests. And although this is something that you will commonly find with IPv4, we decided with IPv6 to remove broadcast completely and go to a multicast form of communication instead.
At King Soopers, you never compromise. You get up high quality that's guaranteed fresh and down low prices on over 1,000 items. With quality and savings that add up, King Soopers shoppers never compromise. King Soopers, fresh for everyone.
Organic and dairy-free.
Here we go.
At Sprouts, our shelves are filled with new, exciting, and delicious discoveries. This is that Sprouts feeling.
If you connect to a network at work or at home, then you're probably very familiar with wireless networks. You may have also noticed that no matter where you go with your wireless device and whatever network you connect to, you always seem to have the required connectivity. This is because there is an international standard for a wireless network that's managed by the Institute of Electrical and Electronics Engineers, or the IEEE. The IEEE standard for wireless networks is in their standards committee for the 802 series, specifically 802.11. So anytime you hear anyone mention 802.11, they're referring to the standards associated with wireless networks. Another interesting characteristic of wireless networks is that they are constantly evolving and constantly changing. So you'll want to check in with the IEEE standards to see which type of wireless network you're using. There's another organization involved with wireless networking called the Wi-Fi Alliance, and you'll notice there's a Wi-Fi trademark logo on every device that the Wi-Fi Alliance has tested. This ensures interoperability with the standards that are set by the IEEE. In the past, we used to refer to these wireless networks with their standards name. For example, 802.11b or 802.11ax. We've recently added additional names to these standards to make them a little easier to understand for everyone who's connecting to these wireless networks. For example, if you're using the 6th generation of Wi-Fi networks, then you're connecting to an 802.11ax network. But we also refer to this network as Wi-Fi 6. This chart shows a list of all of the major Wi-Fi standards listed by their 802.11 name. I've also included the new generational name for those standards, the frequencies they happen to use, and the maximum theoretical link rate for each of those standards. The first three of these standards, 802.11a, b, and g, are rarely used today, and we did not formally set a generation name to those, although you could colloquially refer to these as Wi-Fi 1, Wi-Fi 2, and Wi-Fi 3. The newer standards of Wi-Fi 4 through Wi-Fi 7 are covered through the standards of 802.11n through 802.11be. You'll also notice there's a difference on the type of frequencies that are used for each of these standards, and most of these refer to the 2.4 gigahertz, the 5 gigahertz, and the 6 gigahertz ranges. There are a number of differences on how these wireless standards can be implemented. There might be a different number of antennas or a different number of radios, and that accounts for the differences in the theoretical link rates that you see in this final column. Notice as we've introduced newer standards of wireless networks, that we've also increased the overall link rate of those networks. But we use more than our local 802.11 networks for wireless networking. If you have a mobile phone or a mobile tablet, then you're probably using a wireless provider's network that uses 4G, LTE, or 5G technologies. LTE stands for long-term evolution. It is what we refer to as the 4G technology, and it was a conversion between different standards of GSM and CDMA into a single standard that every provider can use. These 4G networks supported download rates of approximately 150 megabits per second, and the improved version of LTE, which is LTE Advanced or LTE-A, supports download rates that double that to 300 megabits per second. A more modern version of mobile networking is the 5G networking that was introduced in 2020. This greatly improved the performance of wireless mobile networks, and with the right configuration, the goal will be to have 10 gigabits per second as the overall throughput. And in other implementations, you may see more reasonable speeds, such as 100 to 900 megabits per second. 5G has dramatically changed the way we look at mobile connectivity, especially since we're now able to get similar bandwidths over our mobile providers that we currently have with wired network providers in our own homes. This also means that we're able to greatly increase the size of our Internet of Things, or IoT footprint, because now bandwidth is no longer a constraint. This means we can transfer much more data over a shorter period of time. We can receive notifications much faster than we could in the past. And because we can transfer more data, we can process more of that data in the cloud. There may be times when an organization might have a remote location that is not accessible through any type of traditional internet connectivity. For that reason, we may want to use a non-terrestrial form of connectivity known as satellite networking. This means that we can add a satellite dish to a location and begin sending and receiving data from the satellite. This obviously adds additional cost and complexity, and the speeds of satellite networking, although reasonable, are not as fast as those we might have for traditional terrestrial-based networking. For example, satellite networking commonly provides you with 100 megabits down, 5 megabits up. This means that if you have a remote site that has no other way to communicate, you can add a satellite dish to the roof and begin communicating directly to the internet. As you can imagine, there is a delay as information is sent into space and back down to Earth again. Traditional satellite networking provided 250 milliseconds up and 250 milliseconds down, so each conversation to and from the satellite took approximately half a second. Newer technology such as Starlink advertises a 40 millisecond latency, and they're working to decrease that down to 20 milliseconds. Another challenge with satellite networking is that it requires a direct line of sight to the satellite that's in orbit above the Earth. This means if anything does get between the satellite receiver and the satellite, then we may have a decrease of performance or lose connectivity altogether. For example, if a thunderstorm was to come through, we would suffer through what we call rain fade, where we lose connectivity while that storm is going over. In those situations, it may be necessary to wait for the storm to blow through, or we may have other forms of connectivity that we might use when a storm is currently active.
With Okta, we're fast and safe. Hello security without trade-offs.
Those eyes, that nose, your hair, your Nana's smile, Granddad's sense of humor, Dad's ear for music, and your mom's work ethic. We all inherit things from our families, but what many of us don't, the wealth needed to buy our first home. Progressive wants to help, so we created a down payment assistance grant for first-generation home buyers. Visit progressive.com/open the house to learn more.
If you've connected your computer to a wired network, then you're probably using Ethernet. Ethernet is the most popular networking standard in the world, and almost any device you use will be able to connect to an Ethernet network. There are also many different types of Ethernet. They vary in speed, the type of cabling we use, the connectors at the end of these cables, and the type of equipment that's required to connect all of these devices together. Our modern Ethernet networks have many different standards for both twisted pair copper cabling and for fiber optic connectivity. The reason we're able to connect any device in the world to any Ethernet network and be able to have this connectivity is because there is a single set of standards for all of these Ethernet networks. Those standards are created by the IEEE 802.3 committee. IEEE is the Institute of Electrical and Electronics Engineers, and they're responsible for designing and documenting the standards we use to connect all of these Ethernet networks together. For example, a very common Ethernet network would be 1000 base T. This is a gigabit Ethernet network that operates over twisted pair copper cabling and operates at a speed of 1 gigabit per second. A newer version of that standard is the 10G base T, or the 10 gigabit Ethernet network. This also uses twisted pair copper cabling and operates at a speed of 10 gigabits per second. There are also Ethernet networks that use fiber optics. An example of that would be 1000 base SX, which is a gigabit Ethernet network that uses fiber optics and operates at a speed of 1 gigabit per second. This is just a sample of a few of the more popular Ethernet standards, but there are many Ethernet standards to choose from using different types of media and supporting different speeds. The IEEE has told us that the names they use for these standards don't necessarily correlate back to the details of the standard, but there's usually some information that we can discern from the name itself. For example, if we look at a standard such as 1000 base T, we should be able to break that term apart and determine what type of media and technology is used as part of that standard. For example, the number that's used in the name of the standard is often related to the speed of the standard itself. For example, the 1000 base T, that 1000 refers to the 1000 megabits per second or 1 gigabit per second overall speed. If this standard started with 10G, then it would be related to a 10 gigabit per second network. We often see the term base in the name of the standard. That's referring to the term baseband, which means there's a single frequency that is used to be able to send this data over the network. This is in contrast to something like broadband, which uses many different frequencies to be able to communicate across that network. And very often you can determine what type of media is associated with that standard by looking at the additional letters at the end of the standard. For example, 1000 base T has a T at the end, and we can assume that that T means that this is twisted near copper. If there was an F at the end, it's very possible that this particular standard would use fiber optics. There may be additional letters at the end of the standard. For example, if there is an SX at the end of the standard, it might be referring to a short wavelength light that is sent over that fiber optic connection. As mentioned previously, the IEEE tries to put the name and terms within the standard so that it would be recognizable. That is not a requirement for the name of the standard itself. If you were interested in the details of what that standard supports, you would need to read the entire standard and not just look at the name of the standard.
Tackling your security concerns starts with a prompt. With Sola AI, you get answers to the security questions you really care about instantly. Get started with Sola, the AI you need to get security done.
I used to run out of my liquid detergent so fast because it's mostly water. And that's why I switched to Tide Power Pods. They're pre-measured to meet the cleaning needs of today's big machines. Look how big they are. They are packed with 4 times more cleaning power and 2 times more odor fighters. Skip those costly pre-treaters. These Tide Power Pods deliver mega Tide cleaning. I love the smell of Tide clean. If it's got to be clean, it's got to be Tide.
Many of us are accustomed to using twisted pair copper, especially if we have networks that we use at home or even at our office. But you may occasionally have a need for fiber optic connectivity, and that fiber optic connectivity allows you to send traffic across the network using light. These are often used on very secure networks because it is very difficult to tap into a fiber optic connection without having some type of notification. This is very different than a copper-based network, which uses RF and is relatively easy to tap and gain information from. Fiber optics are also used over very long distances because the signal doesn't degrade as fast as a radio frequency might. So the same signal that we can send over 100 meters of a copper network might be able to be sent over kilometers if you were using fiber optics. And of course, light is not susceptible to any type of radio frequency interference. And if you're working in an environment where there is interference, you might want to use fiber optics to avoid any type of problem with your network. Just as there are many different standards and many different connectors for copper-based networks, there are also many different standards and connectors for fiber optic networks as well. So you'll want to check the configuration and documentation of your devices and make sure that the fiber optics that you're connecting are using the right type of fiber and the right type of connector. If we were to deconstruct a fiber optic cable, you would have something very similar to this. On one side of the cable is the light source. This might be an LED or a laser, and on the other side is the receiver. This LED is sending a light through this fiber optic. That consists of a core that is very reflective, and you can see the light bouncing through this core as it receives on the other side. Around the core is a low reflective cladding, and the entire fiber optic run is protected with a buffer coating around the outside. Here's the connector that's at the end of a fiber optic cable. It has a protective ferrule around the outside of the fiber, and if you look very closely at the very middle of this connection, you can just barely make out the core of the fiber that's in the middle. I'll highlight it here so that you can really see where that happens to be. Let's remove that highlight. Now you can start to see that discoloration where the fiber is connected on the end of that cable. We will generally install one of two different types of fiber optic cables. One is a multi-mode fiber and the other is a single mode fiber. Multi-mode fiber is commonly used for relatively short range communication. This would be up to around 2 kilometers in distance. And often this uses an inexpensive light source such as a light emitting diode or an LED. The core of the fiber optic is relatively large, certainly larger than the wavelength of the light. And because of that, the light itself can use different modes to be able to transmit through that fiber. And you can see the different modes bouncing off the edges of the fiber optic cable itself. Because there are different modes that are being communicated through this fiber, we refer to that as multi-mode fiber. If we're communicating over a much longer distance, we may want to use single mode fiber. Some standards of fiber-based Ethernet can communicate up to 100 kilometers without a need to regenerate the signal. Because we're going a longer distance, we may be using a very bright and intense LED, or we may be using laser to be able to extend this signal much further. A single mode fiber also has a smaller core, which can only allow a single mode of light to propagate through the fiber.
People can get crazy trying to stop a cyber attack. Acronis take the headache out of IT security. At Sprouts, our wide open layout invites you in.
I know that.
With healthy around every corner and tasty on every shelf. This is that Sprouts feeling.
Cabling is the foundation of everything we do in networking. Whether you're using a router, a switch, a wireless access point, or any other infrastructure device, cabling is going to be a critical part of that communication. Once the cabling is installed, it's very difficult to uninstall or remove that cabling and replace it with something else. So make sure you're using the right cabling for the right infrastructure. And even if your network happens to be mostly wireless, eventually that wireless connection will need to connect to a cable. So you need to make sure you have the right cables installed in the right place to be able to provide the best possible throughput of your network. One of the most common cable types is the twisted pair copper cable. This is something we use for practically all wired Ethernet connections, and it usually consists of multiple wires twisted together within a single sheath. You'll often see that the cables themselves are paired together. That's because there's often one type of signal on one of the wires and a reverse of that signal on the other wire. You may see this written as transmit plus or transmit minus, or receive plus and receive minus. The reason that we have the same signal being sent in different forms is so that we can recognize and correct if there happens to be any type of interference. This twist in these two wires means that at least one of these wires will always be moving away from interference. This allows us to compare these signals on the receiving end to determine what the actual signal should look like. Another interesting part is that the different cable pairs have different twist rates. So if you look very carefully at an individual cable, you'll notice that some pairs of cables are twisted much tighter than other pairs. One common misnomer that I often hear about cables is that a certain cable has a particular speed. But in reality, the cable doesn't have any speed at all. The copper is literally just sitting there in the cable. The cable itself is supporting a signal, and that signal is allowing us to send a certain amount of data over that particular type of connection. The specific Ethernet standard that you're sending over that wire determines just how much data you'll be able to move across that particular cable. If you're ever wondering what type of cable you should be using for the type of Ethernet network that you have, you should go back to the 802.3 standards. Those standards will specify the minimum cable type that's allowed for that particular standard, and it will specify the type of signal and the total throughput expected over that cable. To be able to easily determine the type of cable that's appropriate for a specific Ethernet standard, we've created a set of standards for the cables themselves. We refer to these standards as a category of cable. For example, you might find category 5, category 6, or category 7. If you check the Ethernet standard, it will specify the minimum category of cable that is required for that particular standard. For example, if you're using 1000 base T, you can look at the 1000 base T standards from the IEEE, and it will tell you that the minimum cable category for that specific Ethernet standard is a category 5 cable. If you install category 5 cable or anything above category 5, it will work properly with the 1000 base T standard. Although twisted pair wiring is very common for our local area networks, another type of Ethernet cable that's very often used is a coaxial cable. This describes a cable where two or more forms within that cable share a common axis. For example, you can see the single wire conductor that's in the middle of this coaxial cable. There's also an insulator, a shielding, and a jacket that are also sharing that same axis. One common type of coaxial cable, especially on our Ethernet and internet connections, is an RG6 cable. If you have a cable modem or you're bringing in a cable modem connection into your data center, it's probably being brought in on a coaxial cable. If we put two conductors inside of this cable type, then we have a twin-axial cable. We often refer to this as simply twin-ax. Twin-ax is a type of cable that you can commonly associate with 10 gigabit per second Ethernet. It's often installed as part of an SFP Plus interface. This allows for full duplex communication over a single cable, but it limits the amount of distance that you can send this signal to about 5 meters. This has a relatively low cost when associated with fiber optics, and very often it has a much lower latency when you compare it to using something like a twisted pair connection. If you're at work and you look at the ceiling, you may notice that you're not seeing the actual ceiling of that floor. Instead, you're seeing a drop ceiling and something like acoustic tiles that is sitting above the actual ceiling. There is a space between this drop ceiling and the actual ceiling. We refer to that space as the plenum. Inside the plenum, we may have network cables, there might be heat sensors, you might have cables for power, and there may be other pieces of the infrastructure that run inside the plenum as well. In some environments, there may be a drop ceiling, and above the drop ceiling may be ductwork where all of the air supply happens to flow. You may have air supplied as part of a heating or cooling system in that ductwork, and there may be return air that's using additional ductwork to go back to that heating or cooling system. Since a plenum implies that there is a shared airspace, in a configuration such as this where only ductwork is used to transfer the air, there would be no plenum. But if there's no ductwork and we share this same airspace with all of our networking cables, then we need to consider that we're using the proper type of network cables in that shared plenum. This would obviously be a concern in a fire, especially if we're using a network cable type that produces a large amount of smoke or perhaps even hazardous fumes if it was to catch on fire. If this was in a plenum, that smoke and those fumes would be distributed to everyone in the building. This means we need to make sure we're installing the correct type of cable if we happen to be installing this into a shared plenum. Ethernet cables have a jacket on the outside of the cable, and many of those Ethernet cables are manufactured with a polyvinyl chloride or PVC manufacturing. If you're putting this cable into a plenum, then you need a plenum rated cable, and that cable is usually manufactured with a fluorinated ethylene polymer, FEP, or a low smoke polyvinyl chloride, PVC. This plenum rated cable is designed to be much safer in a fire than one that is not designed for a plenum. One challenge when working with plenum rated cable is it may not be quite as flexible as non-plenum rated cable. So if you're going around a lot of twists and turns, it may be a bit more of a challenge to install that cable into the plenum. So if you're installing cable into a new building or you're replacing cable in an existing building, make sure you see where that cable is being run and you use the correct type of cable for that location.
At King Supers, you never compromise. You get up high quality that's guaranteed fresh and down low prices on over 1,000 items. With quality and savings that add up, King Supers shoppers never compromise. King Supers, fresh for everyone.
value means more than just a low price. That's why we offer a full line of Whirlpool appliances built to last. Reliable, efficient, and always ready to perform. Quality from Whirlpool. Everyday value from Lowe's. Shop Labor Day deals at Lowe's. We help, you save.
Transceiver is a combination of two words, transmitter and receiver, and these are usually combined within the same piece of equipment or the same component. A transceiver allows for modularity. You may have a switch like this one. You can see there are a number of open interfaces in this switch. You slide in the transceiver that's appropriate for the media or the network type that you would like to use, and now that particular interface will operate with that particular configuration. So if you need a copper configuration for gigabit Ethernet, you slide in a copper gigabit Ethernet transceiver. Or if you need a fiber-based 10 gig connection, you slide in a 10 gig fiber transceiver. This means that you could have every interface on the switch have a different type of media depending on what transceiver you are planning to use. There are different types of transceivers, different form factors, and different transceivers depending on the media. For example, if you are using an Ethernet switch, you need an Ethernet transceiver. If you're using a fiber channel switch, then you will need a fiber channel transceiver. You can't use fiber channel transceivers in an Ethernet switch or vice versa. This means you get to decide what media type works best for your configuration. If you need copper connections, you can use a copper transceiver, and if you need fiber connections, you can use a fiber transceiver. And if you need to change those connections midway through your installation, you can remove the copper transceiver and replace it with a fiber transceiver. This type of modularity often comes at an additional cost, but it does provide you with a way to plug into whatever network type you might need. One common transceiver type is the SFP type. It stands for Small Form Factor Pluggable. For example, you can plug in a fiber SFP and connect your fiber connections to that particular transceiver. But if you needed copper, you could easily slide in a copper SFP and plug in your RJ45 connector. SFPs are commonly associated with gigabit Ethernet, so that's 1 gigabit per second. There is an enhanced version of SFP called Enhanced Small Form Factor Pluggable, or SFP+. They look identical in size to an SFP, but they support much higher speeds, up to 16 gigabits per second. So if you have a 10 gig connection, then you're probably using SFP+. When you're installing equipment into a rack that's in a data center, you have a limited amount of space available. First, the equipment is only 19 inches wide, and the total amount of space available in the rack is limited by the amount of space you have in the data center. So we want to be sure that we can put as much connectivity into a single space as possible. To that end, we've created the QSFP, or the Quad Small Form Factor Pluggable. This effectively allows you to have 4 times the amount of throughput into a space that's very similar to that of an SFP. For example, an SFP in this form would be a Quad Small Form Factor Pluggable, or QSFP, which consists of 4 channels of SFP. So if one SFP is a 1 gigabit per second connection, a Quad SFP would be compatible with a 4 gigabit throughput. The same thing applies for the SFP+. There is a Quad SFP+, that is a 4-channel SFP+. Since it's common to see a 10 gigabit connection on a single SFP+, a Quad SFP+ can support 4 of those for a total throughput of 40 gigabits per second. This is where we start to see a benefit not only in the amount of space that we're using inside of these devices, but we can take a single fiber connection and effectively extend 4 separate links over that single fiber. There's cost benefit there for equipment and for the media itself. Although the names are very similar, the form factors are slightly different between an SFP and SFP+, and a Quad SFP or Quad SFP+. On the left is an SFP or SFP+. Both the SFP and SFP+ use the same form factor, although the transceivers are obviously very different. The Quad SFP or Quad SFP+ also share the same form factor, but you can see it's slightly larger than the traditional SFP or SFP+. Although it is slightly larger than an SFP, it's not 4 times the size of an SFP, so we are getting an efficiency in space by using a quad SFP or quad SFP plus.
Building your cybersecurity stack isn't rocket science. Simply create your own security apps with Solar. Get answers to the security questions you really care about and act on them instantly. Set up custom alerts, build workflows, or create dashboards. And guess what? No code needed. Don't want to DIY that ish? Sola's app gallery has plug-and-play apps ready for you to use. And with Sola AI, you get your own super talented security wingman. It can do all the work for you. Whether you just need to tie together some loose ends or build up your security stack, Sola's there for your needs. It's simple, quick, and free. Get security done with Sola.
Progressive's Up-Payment program provides down payment assistance for first-generation home buyers. Because we believe everyone should have the access and opportunity to own a home.
When working with fiber optics, one of the first things you'll notice is there are many different connector types. You have to make sure that you use the right connector type for the right connection. A very common fiber connector type is the SC connector, or the subscriber connector. We also have other names that we associate with this connector. One is a square connector, because the connector itself is rather square when you look at it. You might also see this referred to as a standard connector, although there are certainly other types of fiber connectors that you might use. To use an SC connector, it simply pushes into the connection and snaps in place with a lock. Once you have that connector in place, it's not going to accidentally slip out of that connection. You first have to pull on the connector to unlock it, and then it can be removed from that interface. This is a common connector type, and if you're plugging into a connection in a data center, you're probably using some connections that are identified as SC. The connectors themselves support individual fibers, but they're often combined together into a pair because one of these is commonly used for transmit and the other is commonly used for receive. Another common fiber connector is the LC, or local connector. This is slightly smaller than an SC connector, and as you can see, it has a clip on the top to lock it in place once you put it into the interface. This also means that it won't accidentally get pulled out of an interface, and to remove it, you need to push down on the clip. That will release the lock and allow you to easily remove it from the interface. Instead of local connector, you might also see this referred to as a lucent connector or a little connector. The LC connector can also be combined in a pair, looks like this, and you can plug both of them in simultaneously, and again, one is used for transmit and the other used for receive. Another fiber on our list is the ST connector, that stands for straight tip. It uses a bayonet connector, so you push it into an interface, give it a slight twist, and it is locked in place. This will not easily get removed from the interface unless you reverse that twist, and then you can remove it from the interface. When you're working inside of a rack and there's a large number of cables and fiber, it can be very easy to accidentally dislodge one of those connections. That's why we have all of these different locking mechanisms for these different interface types. Here's a closer view of the ST connector. There is a protective ferrule around the fiber, which you can barely see in this picture, and you can easily see the bayonet connector where you would plug it in and twist it in place so that it is locked into that interface. One of the challenges with the connector types that we've seen so far is that those fiber connections take up a lot of real estate. It would be a lot more efficient if we could put more fiber into a smaller connection, and there is a connector type for that called the MPO, which is multi-fiber push-on. Inside the MPO are 12 individual fibers that are contained in that single cable connection. This also has a lock in place that's very similar to the SC connector, where you would push it in place and you would have to pull it out slightly to unlock it from the interface. You might also see this connector referred to as an MTP. That name is provided by Corning, and they refer to this as an MTP MPO connector. Here's a side view of the connector. It has this lock on the top, and the individual fibers are these smaller dots you can barely see in this picture. If we look at it straight on with some light being sent through the fiber, you can see that all 12 of those fibers are much easier to see, on the MPO connector.
People can go crazy trying to stop a cyber attack. Acronis take the headache out of IT security.
Your Unstoppable is a limited collection. Luxury laundry scent beads so you can smell unstoppable.
One common copper connector we use on our networks today is an RJ11. It stands for Register Jack Type 11. It is a 6-position connector, but we only use 2 conductors inside of this connector. Sometimes you'll see this referred to as a 6P2C, or 6-position 2-conductor. We commonly associate an RJ11 connector with an analog telephone, but you'll also see RJ11 used for DSL connections, since those use exactly the same wires as a telephone connection. Here's a better view of the RJ11 connector, and you can see the 6 positions, 1, 2, 3, 4, 5, 6 are clearly marked, but you notice that there are the 2 conductors in the middle that are used for RJ11. If you're using an Ethernet connection, then you're using an RJ45 connector, and this stands for Register Jack Type 45. It is an 8-position connector with 8 conductors inside, so we're using all of the conductors available on an RJ45 connection. This is slightly larger than an RJ11 connector, and it's what you would use if you're plugging in an Ethernet connection. Here's a device that has both RJ11 and RJ45 connectors on it. You can see this is a DSL connection that uses the RJ11, and these LAN connections or Ethernet connections are using the RJ45. You can see that they're very similar in shape, although the RJ11 is slightly smaller than the larger and wider RJ45. If you're using a cable modem connection, then you're probably bringing coax connections and plugging it into a cable modem. And the connector that you're probably using is the F connector. The F connector is a standard connection type. It usually has threads inside that allow you to fasten it very securely to the connector. And if you are using a cable modem, this is probably the connection type that you're using from the cable television infrastructure. This is also referred to as a DOCSIS connector, that stands for Data Over Cable Service Interface Specification. The connection that brings the signal is this single copper connection on the inside of the cable. This is what you would plug in and screw into a cable modem using that F connector connected to the coaxial cable. Another common connector used for coax is a B and C connector. This is a bayonet connector, that's what the B stands for, where you push it into the connector and twist it slightly to lock it in place. The NC in the B and C connector stands for Neil Conselman. This stands for Paul Neil from Bell Labs and Carl Conselman from Amphenol. They both were involved in creating this standard for a B and C connection. If you're bringing in a WAN connection or any other type of coax, it's very possible you might use a BNC connection to lock this in place. That is one of the benefits of using BNC, is that you're able to push the connector in and twist it, and it's not going to easily remove itself from that connection. You would need to untwist before removing that from the interface. Here's a close-up view of the BNC interfaces on a device. You can see where you would plug in the BNC connector, you twist that connector slightly, and it's locked in place onto that device.
Nature's Bounty. Nature's Bounty supplements your journey with advanced menopause relief by helping relieve the 12 most common symptoms, including hot flashes. It's in your nature to evolve.
Networks can connect to each other in many different ways, and in this video we're going to look at a number of different network topologies and how those different network topologies can be deployed in an enterprise network. This can be very useful during the planning process where you're designing the network. It's also useful during the troubleshooting process so that you can tell how different networks are connected to other networks. This is also useful during the troubleshooting process so that you can visually see how one network might connect to and send data to another network. Let's start this conversation with one of the most popular network topologies in use. That would be a star network, Sometimes you may hear this referred to as a hub and spoke network. This is what we use in most large networks to connect devices together. There's a central device that is used as the central networking component, and then everyone on the network is all connecting to that same central device. A good example of a star network or a hub and spoke network is one that we have with switched Ethernet. Our Ethernet switch sits in the middle of the network, and all of the other devices connect to that same Ethernet switch. If each of these spokes around the network would like to communicate with each other, they all must communicate through this central hub. A mesh network design is if one location or device connects to another location or device over more than one network connection. This means that we could have one link communicating to another, and it might follow one path to get to that location, or it may follow an alternate path to be able to get to that location. One reason we design a network this way is so that if one link in the mesh was to fail, we can use one of the other links to complete that communication. We might also perform load balancing over these links where half of the data is sent over one connection and the other half of the data is sent over a different connection. Although we can certainly design mesh networks for local area networks, we often see them deployed in wide area networks so that we can maintain connectivity to a remote site regardless of what network connection might be available. If you were to look at a large enterprise network, you would notice there are a number of different architectures all being used in different parts of the network. And when we combine all of those together, we've created a hybrid network. One part of the network might be a star network, another part of the network may be point-to-point, and a third part of the network might be a mesh network. Once we combine all of these together, we've created a hybrid architecture. Many data centers take advantage of a spine and leaf architecture. This is where you would have individual switches at the top that are the spine of the network. There would be switches in the middle that are leaf networks, and then you would have different devices connect to the leaf. You'll notice that the spine network is connected to all of the leaves, and the leaves are connected to each of the spines. However, those leaf switches do not connect directly to each other, and the spine switches also do not connect directly to each other. This works very well for an architecture we use in many data centers known as top-of-rack switching. In top-of-rack switching, every rack has a leaf switch at the top of every physical rack. We would then connect all of the physical devices in that rack to the leaf switch that is at the top of that rack. This keeps your cabling very simple because all of your cabling is self-contained within that same rack. There is redundancy because you have this rack connected to multiple spines. This also increases the overall performance of the network because we're no more than one switch away from any other device in the data center. If your data center only has a handful of racks, this may be a relatively inexpensive way to connect all of these devices together. But when you have tens or hundreds or even thousands of racks in a data center, you would need a separate switch for every rack, and of course the cost of that will increase for each rack you have in the network. When looking around the network, you may find some wide area network connections that are point to point, and as the name implies, there is a single point connected to a single point. This was a very common design on older wide area networks where you would use something like a T1 or a T3 connection. We refer to those as point-to-point T1 or point-to-point T3. We might also use this design in local area networks. If you work on a campus, you can connect one building to another over two connections, and the connection between those two buildings would be a point-to-point connection.
Cybersecurity today is so messy and expensive. And why does it take so long? It really shouldn't be that. Get started with Sola, the studio where you can build any security app. Whether you're the security person or just the person tasked with security, tie together some loose ends or build up your security stack. You fit Sola to your needs. It's simple, quick, and free. Get security done with Sola.
Spending time with the ones you love is priceless. That's why Kroger Delivery, proudly serving King Soopers, makes grocery shopping effortless. Get $20 off your first order. We'll deliver your groceries in our refrigerated trucks and bring them to your door. King Soopers, fresh for everyone.
Many enterprise networks take advantage of a three-tiered architecture. This is a very common design, and you'll find many organizations use a three-tiered network design for their network. This starts with the core of the network, and this is where we might have the central point for all of our resources. So our servers, our applications, our databases, and other critical points are going to be contained within the core of the network. The second tier in a three-tiered architecture is the distribution layer. This distribution is the midpoint between the users and those core resources. This is usually a series of switches that provides redundancy and connectivity for those users to access those critical resources. And lastly, our users need somewhere to connect, and they often connect to an access layer. These are switches that are usually located very close to the user, usually on the same floor of a building, for example, and that access layer allows us to connect to the distribution, which then connects to the core of the network. This three-tiered architecture is very common to what we might see in a large city. The downtown area of the city is the core of the city, and all of the major resources for that city may be located in a very small geographical area in the center or core of that location. To be able to get to downtown, we need some type of distribution method. For example, we need some type of highway that might connect our homes to the downtown area. And our homes are usually connected to these larger highways through access roads. This allows us to use our local roads for all of our daily chores, but when we need to get to the core downtown, we may need to use those distribution highways. Here's what this three-tier architecture looks like in a network diagram. The core of the network usually has core routers that are allowing us to connect to other resources in the core. The distribution layer in the middle is the one connecting the core to the access switches. And at the very bottom, the access layer is the one that all of the users are connected to. You'll notice there are multiple links between the access and the distribution, and occasionally you might even find multiple links between the distribution and the core. So if one component happens to fail, we can always use other parts of the network to complete that communication path. This is often combined with multiple buildings. So here on a single campus, we have two separate buildings. All the users are connected on each floor of the building to an access switch. Each access switch in the building is usually connected to one or more distribution switches, and those distribution switches are connected to the core of the network, which may be located in a central data center. If you're a smaller organization, there may not be a need for a much larger three-tiered architecture. Instead, you might want to use a collapsed core architecture. This is a two-tier architecture that combines the core and distribution layer into a single collapsed core. You can see the access layer is still exactly the same as it was before. This allows for a more simplified design and hopefully a much easier design when you're troubleshooting. This is also a lot less expensive to implement because you have less devices that you have to purchase and install onto the network. However, as you can tell by this diagram, there's not a lot of options for redundancy, so this may not be quite as resilient if you happen to lose any of these individual components. When you're describing the flow of traffic within a data center, it's important to know where the traffic originates and what the destination is for that traffic. One way to describe traffic flow is an east-west traffic flow. This means that the origination and destination for this data flow is all within the same data center. This also means that we probably have very good response times from one device to another since they're all located on the same local network. If the traffic flow is one that is leaving the data center or is coming into the data center from an external source, you would refer to that as north-south traffic. This would probably have a bit of a different security posture than something that is east-west traffic because we really don't know where this traffic is going once it leaves the data center, and any inbound traffic could be coming from potentially anywhere. Here's a better view of this traffic type. If data is coming into the network from the internet or we're sending information out to the internet, we refer to that as north-south traffic. Any traffic that is inside this local data center, for example, if we have a file server that is sending information to an image server, all of that traffic is staying within the data center and would be considered east-west traffic.
Those eyes, that nose, your hair, your Nana's smile, Granddad's sense of humor, Dad's ear for music, and your mom's work ethic. We all inherit things from our families, but what many of us don't? The wealth needed to buy our first home. Progressive wants to help, so we created a down payment assistance grant for first-generation home buyers. Visit progressive.com/openthehouse to learn more.
In the next part of this course, we're going to talk a lot about IP subnetting. And a big part of subnetting is the ability to convert between decimal and binary. So I thought it would be useful in this video if we step through the fundamentals of performing binary calculations. Binary, of course, is a type of numbering that uses two different numbers, either a 0 or a 1. This means that there are only two possible options when doing mathematics in binary. The answer is either going to include a 0 or it's going to include a 1. Each one of these zeros or ones is referred to as a bit. And when we combine 8 of these bits together, we have a byte. Occasionally you will see a byte referred to as an octet to be sure that everyone understands that this is an 8-bit byte. In this video, we're going to perform a lot of calculations between binary and decimal. So what we need to create is a conversion chart to convert between binary and decimal. We'll create this chart by starting on the right side, and we'll simply put the number 1. Then we're going to double that number and put it to the left. So doubling 1 makes the number 2. If we double the number 2, we have the number 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32, and so on. This is the conversion chart that we will use for almost all of our decimal to binary conversions. We created this chart with 8 individual places, but you could keep moving to the left with this chart and go past 128. We'll double it to 256. We'll double that to 512, and so on. You can keep continuing this process so that if you have a very large binary number, you can still perform the same type of conversion back to decimal. Let's now use this chart to answer this question. What is the binary 00000010 in decimal? First, let's write down this value in decimal. So it's 00000010. And of course, we want to know what the decimal equivalent is of that binary value. We'll then layer on top of this our conversion chart. So of course, we start on the right side with a 1, then 2, 4, 8, 16, 32, 64, and 128. Now we have everything we need to perform this binary calculation. In each of these places where we have a binary 0, we're going to bring that 0 down to the bottom line. In every place where we have a binary of 1, we're going to take the number just above that and bring it down onto the bottom line. We're then going to add all of these numbers together on the bottom line. So 0 plus 0 plus 0 plus 0 plus 0 plus 0
Welcome
plus
back from lunch,
0
everybody.
equals 2 in
Good to
decimal.
see you.
So the answer to this question of converting binary 0000
So, Elaine,
00
hear anything
10
back?
is the same as 2 decimal. Let's do another one. What is the binary 10000010 in decimal? We will write down.
No, haven't heard anything back so far. I think we might have to. I'm not sure how long they're gonna take.
Gotcha. So what we're gonna do is I'm gonna send you your voucher number. I just want to see if you can reschedule. If you can get in CompTIA, or if it disappeared. Let's see.
binary value, and then we'll layer on top of that our conversion chart. Every place there's a 0, we're going to pull that down and put a 0. And every place there is a 1, we're going to pull down the number just above that 1. And you can see we only have 2 binary 1s in this number, and that's associated with the 2 and associated with the 128. So we'll bring down the 128, we'll bring down the 2, we add those together, and we've got 130 in decimal. So the binary value 10000010 is the same as 130 in decimal.
Getting everyone in your home on the same page about energy use is hard, so we're making it easier. Excel Energy offers programs and services like a home energy assessment and smart thermostat rewards, plus rebates to help reduce the cost of energy upgrades in your home. We make energy decisions easier. Who gets to control the remote? That's up to you.
It's my first day at school. I can't let anyone know my secret. Vampirina, are you awake?
I can't believe today's the day.
Your father's just a little nervous because the world is full of vampire hunters. You get nervous?
I sent your voucher number in private chat, so if it disappears, see if you can try that number again. Maybe they released it and you can use it again to reschedule for this week.
Whoa! She scared me. Me? Scary? No. Surprise! What are you doing here?
And finally, let's do one more binary to decimal conversion. This binary value is 11111111. We'll bring down that binary value and we'll layer on top of that our conversion chart. And because each one of these spaces has a 1, we're going to bring down all of the numbers of our conversion. And if we were to count 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, you would have the value of 255 decimal. So the conversion of 11111111 in binary is the same as 255 in decimal. Now let's do the same conversion, but in reverse. Let's take a decimal number and convert it to binary. This question asks, what is the decimal 154 in binary? It's the same process. We're going to bring down our binary number, but of course we don't know what that binary number is yet, so we'll put some place marks here, and then we'll layer on top of this our conversion chart. Now we need to determine which one of these binary values will be a 0 and which one will be a 1 to make up 154 decimal. And there's only one combination of 0s and 1s in this chart that would equal that decimal value. We'll start on the right side where we have our 128 column, and we'll ask ourselves, is 128 less than or equal to 154? This is obviously less than 154, so we'll put a 1 in that column, and we'll bring down the 128. Now let's look at our next column of 64, and we'll combine that next column with the numbers that we've currently brought down previously. In this case, the number 128. So 128 plus 64 is 192. And we have to ask ourselves, is 192 less than or equal to 154? In this case, 192 is more than 154, so the answer is no, and we'll put a 0 in that column. Now we move to the next column, which is our 32. We'll add 32 plus anything that we brought down. That would be 128 plus 32, which equals 160. Is 160 less than or equal to 154? It is not, so we'll bring down a 0 in that column. We'll continue with this process by looking at the fourth column, which is 16. We'll add that to anything that we brought down. So 128 plus 16 is 144. Is 144 less than or equal to 154? It is, so we'll put a 1 in that column and bring down the 16. Our next column is the 8, so we'll add 8 to anything that we've previously brought down. So 128 plus 16 plus 8 is 152. Is 152 less than or equal to 154? It is, so we'll put a 1 in that column and bring down the number 8. Our next column is the number 4. We will add 4 to everything that we brought down into that bottom row. So that all adds up to 156. And is 156 less than or equal to 154? It is not, so we'll put a 0 in the 4 column. The next column is the number 2. We'll add the number 2 to everything that we brought down so far. And if we add all of those up, it would be 154. Is 154 less than or equal to 154? It's obviously equal to 154. So we'll put a 1 in that column and bring down the number 2. And obviously we've hit the number 154, so we know that the number 1 on the last column will not be added to this final value. And if we add up everything in that last row, we see it does equal 154. And now all we have to do is look at the middle row to determine what the binary value of this is, and it would be 1001, 1010. If we look at 154 decimal, we know that that is exactly the same as 1001, 1010 in binary. With these 8 individual bits, we can convert any number between 0 and 255. So take any number you would like, put it into this particular format, and see if you can perform the conversion between binary and decimal. As you're increasing the number of bits in a binary value, you're increasing the total possible number of decimal results. For example, if you have 2 bits, there are only 4 possible outcomes: 00, 01, 10, and 11. And if you were to perform that conversion between binary and decimal, that's the same as 0, 1, 2, and 3. If you have 3 bits, then you can have 8 possible outcomes. If you use 4 individual bits, you have up to 16 different options. 5 bits moves you up to 32, 6 would be 64, 7 bits is 128 possible options, and if you were to increase the number of bits into 9 bits, 10 bits, 11 bits, and so on, you would also increase the total decimal number. You can see that this value is listed in this chart, and notice that I've also added the powers of 2 on top of this. This is effectively what we've been doing the whole time. 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and so on. So as we increase this powers of 2, we are also increasing the total decimal value.
Building your cybersecurity stack isn't rocket science. Simply create your own security apps with Sola. Get answers to the security questions you really care about and act on them instantly. Set up custom alerts, build workflows, or create dashboards. And guess what? No code needed. Don't want to DIY that ish? Sola's app gallery has plug-and-play apps ready for you to use. And with Sola AI, you get your own super talented security wingman. It can do all the work for you. Whether you just need to tie together some loose ends or build up your security stack, Sola's there for your needs. It's simple, quick, and free. Get security done with Sola.
If you've done anything with networking, then you've probably run into an IP version 4 address. In this video, let's look at the different configuration options for IP version 4. The IP address is the unique identifier that every device on the network must have if it wants to communicate using that IP protocol. An IP address is a series of 4 numbers separated by a period. This would be something like 192.168.1.165. To be able to properly communicate on the network, every device needs to have its own unique IP address. The IP address is combined with another value referred to as the subnet mask. The subnet mask is also a 4-octet value, for example, 255.255.255.0. The subnet mask is used in conjunction with the IP address to determine what IP subnet this particular device is on. This isn't something that's usually transmitted across the network. It's instead used by your local device to make the determination of what devices are local on this IP subnet and what IP addresses may be outside of this local IP subnet. This becomes especially important when you need to send traffic outside of your local subnet, and you do that through the use of a default gateway. The default gateway is the IP address of a device that's on your local subnet that allows you to communicate outside of this subnet. For example, if we have an IP address of 192.168.1.165 and a subnet mask of 255.255.255.0, a common default gateway could be 192.168.1.1. This is an IP address that is configured and assigned to the router on your local subnet by your network administrator, and it must be an IP address.
Ryan, are you there?
Network. There are also other IP addresses you should be familiar with. One of these is a loopback address. This is a way to define your local device without having to know a specific IP address. Every device on the network has a loopback address, and it's a number that is between 127.0.0.1 through 127.255.255.254. So if you wanted to ping your local device, you could ping 127.0.0.1, and hopefully your local device would be able to respond to you. This is often used to confirm that your local IP stack is working properly, and it would then be able to communicate to other devices. We also have a range of IP addresses that we've set aside as reserved addresses. This is a range of IP addresses that should never be assigned to other devices. They're used for future use or for testing in the future. This range of reserved addresses is 240.0.0.1 through 254.255.255.254. Anything that is a Class E address is also a reserved address. We'll talk about classes of addresses in just a moment. And another address type you might run into is one that is not real. It's a virtual IP address, or a VIP. Virtual IP addresses are not associated with a physical Ethernet adapter. Instead, VIPs are addresses that you would assign to the internals of a device so that you can always reference that device using that virtual IP address. For example, you might assign a VIP to a virtual machine, or the VIP may be an internal address that you're associating with a particular router. The IP protocol and IP version 4 operate at OSI layer 3. So anytime you're working with an IP address, you're working at that network layer of the OSI model. Let's break apart an IP version 4 address and really see what it's made of. Let's take the address 192.168.1.131. We refer to these 4 values as octets. That's because they consist of 8 individual bits. And you can see the representation of that same IP address broken out into those 4 groups of 8 bits. Sometimes you'll see these 8 bits broken out and described as 1 byte or sometimes 1 octet. So if you were to count up all of these bits, there are 32 total bits in an IP version 4 address, and that is the same as 4 bytes or 4 octets. Since each one of these individual groups inside of IP version 4 consist of 8 bits, the maximum value that you would ever have in decimal for any of these groups would be a maximum of 255. In the early days of networking, we had to manually configure the IP address, subnet mask, and default gateway all in a manual way. We had to visit that device, change a configuration file, and then that device would be able to communicate on the network. If anything changed with our network configuration or we needed to change the IP address of that device, we had to revisit the device and manually make those changes. Today, of course, we can plug in any of our devices and it automatically receives an IP address. The way that we are able to receive this automated IP addressing is through a protocol known as DHCP, or Dynamic Host Configuration Protocol. When we plug into a wired Ethernet network or a wireless network and we're automatically able to communicate out to the internet, it's because we've received all of our IP configuration settings via DHCP. But if you've ever connected to a network that does not have a DHCP server, you may notice that you're still assigned an automatic address. But this address is not quite as capable as a DHCP address. Instead, it's what we call a link local address because it can only communicate to other devices that are on your local subnet, and we cannot route that traffic outside of your local subnet. For example, if you're assigned a link local address, you can't communicate to the internet because that's outside of your local subnet. In IP version 4, this link local address is assigned through a process known as Automatic Private IP Addressing, or APIPA. This range of IP addresses automatically assigned through APIPA is 169.254.0.1 through 169.254.255.254. There are also reserved sections of that range. The first and last 256 addresses are reserved and they're not assigned to end stations. So if you receive an APIPA address on your device, it's between 169.254.1.0 through 169.254.254.255. Just as DHCP works automatically to assign your address, APIPA also has an automated process to assign this address. It uses ARP to confirm that no one else on your local network has that link local address. And if nothing responds to that address resolution protocol query, then it will assign a random number between that functional block. One of the challenges of IP4 is that there are far more devices in the world than there are IP4 addresses. And in recent years, we've used up all of the available blocks of IP version 4 addresses. There are no other IP version 4 addresses that can be assigned in these blocks.
When he gets back, we'll give him a big hoorah.
To be able to communicate via IP version 4. One way that we've been able to extend the functionality of IP version 4 is to create an assignment of IP address ranges that can only be used on the inside of a network. We refer to these as a private IP address range, and anything that is a private IP address cannot be routed on the public internet. Fortunately, these are very large ranges, and we're able to use those ranges on the inside of our corporate networks. If you were to look at the IP address that's assigned to your device right now, it's likely that it's a private IP address. So if your device is currently using a private IP address, and you're watching this video on the internet, how are you able to communicate on the internet with an address that is not able to be routed across the internet? We're able to do that through a functionality called Network Address Translation. This allows us to convert a private IP address into a public IP address and use that public IP address to communicate on the public network. We'll learn more about network address translation as we go through this training course. If you want to learn more about private IP addresses, you may want to reference a request for comment, or RFC. RFC 1918 is the standard that defines these ranges of private IP addresses and how they can be used on our networks. If we were to look into the details of RFC 1918, you would see 3 different ranges have been set aside for private IP addressing. These 3 ranges are 10.0.0.0 through 10.255.255.255. And if you were to count up all of the possible addresses in that range, it would be over 16 million addresses. We often refer to this as a single Class A block of addresses, and we often write it as 10.0.0.0/8. If you were to write out the subnet mask of that /8 address, it's 255.0.0.0. This means the host size of this particular IP address range is 24 bits in length. Another range is 172.16.0.0 through 172.31.255.255. This gives us a total of just over 1 million addresses that we can assign in 16 contiguous Class B address ranges. If we were to write this out in CIDR block notation, it would be 172.16.0.0/12. The decimal subnet mask for a /12 network is 255.240.0.0, which means our host ID size is 20 bits in length. And the last range is 192.168.0.0 through 192.168.255.255. This allows us to assign over 65,000 addresses as part of 256 contiguous Class C address ranges. The CIDR block notation for this would be 192.168.0.0/16, and that /16 subnet mask is the same as 255.255.0.0. Half of this address is assigned for hosts, so your host ID size.
I heard you fast, Dan.
Yes, sir.
The next series of videos.
It's 8:47, that's what I got.
Block notation, the different classes of.
You trying to get audited?
And other details that you see associated with these private addresses.
You get close to 900.
That's crazy. I think
Hey,
it's my experience too.
Yeah, I think so too. Dude, you've been doing help desk forever. Way to go, man. Yeah, look at you, 847. Yeah, CompTIA, when you get close to 900 like that, they be looking at you like, yeah. There's been people that's gotten close to 900, like super close, and CompTIA has sent them an email saying, you need to go back in and take the exam again. They don't erase their score that they got. They just want to make sure that they go in and take it again to see how close to get back. That's how they find out who's cheating. So, like, if your score is like way off, like you go in there and hit up a 860, but they said we need you to go in here Friday, and you knock out a 400, they're gonna be like, yeah, they're gonna be watching.
A Class B address default subnet mask is 255.255.0.
You go to your exam tab on the right.
255.255.255.0.
Yeah.
This style of class-based subnetting is one that we have not used.
And then it should say previous scores or the previous exams. Previous
In a
exams.
very colloquial sense. And although you may hear someone refer to an address as a Class A address or a Class C address, in reality, we no longer use a class-based form of subnet masking. So if we don't use classes, why are we doing a video on class-based networking? That's because these classes do act as a starting point when we begin any type of subnetting on networks.
It'll probably be there tomorrow.
It's important to know where to begin the subnetting process, and this class-based system is the starting point. These Class A, Class B, and Class C addresses have an
Always hold on to that piece of paper until the score pops up in CompTIA.
and the host part of the address.
After that, you can just throw it away from
line is
them.
drawn after the first 8 bits. In a Class B address, that line is after the first 16 bits. And in a Class C address, that line is after the first 24 bits. Here's a table that defines the different subnet classes for Class A, Class B, Class C, Class D, and the reserved Class E. And you can see if you look on the right side, the default subnet masks are the ones we just saw, where Class A has a default mask of 255.0.0.0, Class B is 255.255.0.0, and Class C is 255.255.255.0. The way that you can look at an IP address and tell immediately what class that IP address is associated with is the very first octet of the address. If the decimal octet is between 0 and 127 as the first number of that IP address, it's a Class A address. If the first number of the IP address is between 128 and 191, that's a Class B address. And if the first number is between 192 and 223, that is a Class C address. If you were to look at that address in binary, if the first bit was 0, it's a Class A address. If the first bits are 10, it's a Class B address. And if the first 3 bits are 110, it's a Class C address. Class D addresses are used for multicast communication, and therefore they are not assigned to an individual device. But there is a range for Class D addresses, and that is between 224 and 239, or the first 4 bits of a Class D address are 1110. And there is a range of IP addresses that are not used for any purpose. This is a reserved range. We refer to this as the Class E range, between 240 and 255, or the first 4 bits of 1111. So based on that chart and those ranges of IP addresses, let's see what class a particular IP address would be part of. Let's start with the IP address of 17.22.90.7. To be able to determine the class, we need to look at the first octet, which in this case is the number 17. And if you refer back to that chart, the number 17 is in a Class A address. Let's do another one. IP address is 220.10.77.40. If we look at that first octet, it is 220, and 220 is in the C class. The next IP address is 165.245.0.1. We need to look at that first octet. In this case, that's 165, and 165 is in the range of a Class B address. Next on our list is 128.90.10.2. That first number is 128, which means that is also a Class B address. The IP address of 191.77.24.250 has the first octet as 191, and if we refer to our chart, 191 is in the range of a Class B address. And lastly, 192.1.12.5, we're looking at that first octet of 192, which falls in the range of a Class C address. When you start calculating an IP subnet, there are 4 different values that are very important to know. The first is the IP address associated with the network address. This is the one that defines all of the other devices on this particular subnet. To calculate a network address, you set all of the host bits of that address to 0 and then determine what the decimal representation of that might be. The second important piece of information you need for an IP subnet is the first usable host address on that subnet. This is always going to be 1 number higher than this previously defined network address. You also need to know the network broadcast address. This is the last IP address of this particular network address. To be able to calculate the network broadcast address, you would set all of your host bits to 1, which is the same as 255 decimal, and perform the conversion between the binary and the decimal. And just as you need to know the first usable host address on the network, you also need to know the last usable host address. And to calculate that, you look at the network broadcast address, and it's 1 number fewer than the broadcast address. So let's calculate those 4 important subnet values. And let's start with the IP address of 10.74.222.11. If we look at our chart, we know that this starts with the number 10, therefore this must be a Class A address. And the default subnet mask for a Class A address is 255.0.0.0. Since we're using this Class A subnet mask, we know that everything that's on the left side of our bar, or this first octet, is going to be our network address, and everything on the right side will be associated with the host ID. So let's add those to our chart. We have a network column and a host column. Obviously, the 10 dot is going to be in the network column. That's what's on the left side of that bar. And then everything on the right side is going to be the host address. We first need to calculate the network address, and to do that, we set all the host bits to 0. This means that everything in that second column will be 0, and the network address, therefore, will be 10.0.0.0. The first host address is 1 more than the network address, so our first host address would be 10.0.0.1. To calculate the broadcast address for this subnet, we set all the host bits to 1, which means that the broadcast address is 10.255.255.255. And as you recall, to calculate the last usable address on this subnet, we need to subtract 1 from the broadcast address. So the last usable address on this network is 10.255.255.254. With these 4 values, you'll be able to determine the network address. You'll know if an IP address happens to be one of the usable addresses within that range, and you'll know what the last or broadcast address is for that entire network. Let's do another one. In this case, the IP address is 172.16.88.200. If we look at that first octet, we can see that that is a Class B address, which means the default subnet mask for this network is 255.255.0.0. This means that we would draw our line right in the middle between the first 16 bits and the last 16 bits. So everything on the left side is associated with the network address, and everything on the right side is associated with the host address. Now let's perform those exact same calculations. We want to determine what the network address is, so we will set all host bits to 0. This means that the network address for this particular subnet is 172.16.0.0. To be able to calculate the first host address, we need to add 1 to that value, or 172.16.0.1. To calculate the broadcast address, we set all host bits to 1, which means the broadcast address for this subnet is 172.16.255.255. And to define the last usable host address on this network, we subtract 1 from the broadcast address, which means the last usable address is 172.16.255.254. Let's see if we've figured out this process and step through another IP address, in this case, 192.168.4.77. Looking at this first octet of 192, that fits into the range of a Class C address, which means the default subnet mask is 255.255.255.0. If we were to draw our line, the network side of the address is the first 3 octets, and the host side is the last octet. Let's put that into our chart. So our first 3 octets, 192.168.4 is the network side, and .77 is the host side. To be able to calculate the network address, we set all host bits to 0, so the network address for this particular subnet is 192.168.4.0. If we add 1 to that address, we get our first host address of 192.168.4.1. To be able to calculate the broadcast address, we set all host bits to 1, which means the broadcast address is 192.168.4.255. And if we subtract 1 from that broadcast address, we get the last host address, and that would be 192.168.4.254. Although we no longer use class-based subnetting, we can still use this same process when we look at anything that may be class or non-class based. And as we go through our additional subnetting videos, you'll notice that this same process is used over and over again, regardless of the IP address and the subnet mask.
Organic and dairy-free? Woo! Woo!
In a previous video, we talked about class-based subnetting and how IP addresses can be assigned a Class A, Class B, or Class C address. But since 1993, we've not used class-based subnetting. Instead, we use classless subnetting. Sometimes you'll see this referred to as classless interdomain routing, or CIDR. This classless addressing means that we can assign a subnet mask that doesn't fall into those same Class A, Class B, or Class C arrangements. And instead of referring to the subnet mask in its decimal form, we can simply refer to it as the number of bits. That number of bits is referred to as a CIDR block notation. For example, a decimal subnet mask of 255.0.0.0 is the same as a /8 CIDR block notation because it has 8 individual bits as part of the subnet mask. So it would be very common to see an IP address written as 192.168.1.44/24. Everything with the /24 is referring to the number of bits in a subnet mask, and a /24 mask would be the same as 255.255.255.0. When you're configuring a device, you're often giving it an IP address, a subnet mask, a default gateway, and very often a series of DNS servers. Most of the time, an operating system is expecting you to put the subnet mask in as a decimal mask. So for example,
All right, so
you may put the IP address and then you might add in the
I just
decimal
updated
version
your
of the
tickets,
subnet mask.
so it should
But if
reflect
you're
on your
using a router or a switch, it may be
A+
expecting
certified
the CIDR
on your
block
school record.
notation for
Yay!
those masks. So instead
And then
of
within
using
24 hours
255.2.0.0,
tomorrow, you should see
you would
your
simply input
it should
/8.
pop up
Make sure you check the
in your
documentation
CompTIA
of the
dashboard.
device you're using to see what notation it prefers for the subnet mask. As you've probably seen in our previous examples of subnet masks, the mask consists of a contiguous series of ones followed by zeros. So the ones would be on the left, the zeros would be on the right. For example, here is a subnet mask. You can see the contiguous set of ones on the left and the zeros that are on the right. In this example, you can see 3 separate octets that are set to 1. So there are 24 ones in this particular mask, and there are 8 zeros at the end. If we were to write this out in decimal, it would be 255.255.255.0. And if you were to write this out in CIDR block notation, you would count how many ones are associated with this subnet mask. In this case, there are 24, so the CIDR block notation would be /24. The subnet mask is obviously used to separate the network part of the address from the host part of the address. So for this particular subnet mask, the network address is 24 bits in length, and the host address is 8 bits in length. Let's convert a binary subnet mask to one that is the CIDR block notation for a subnet mask. And we'll take this subnet mask that we have on the screen, which has all ones in the first 2 octets and all zeros in the last 2 octets. If we were to count the number of ones in this subnet mask, we have 8 in the first octet, 8 in the second octet, none in the third, and none in the fourth. That means the total number of ones in the subnet mask would be 16, so the CIDR block notation would be /16. This means that the first 16 bits of the subnet mask are associated with the network, and the last 16 bits are associated with the host ID. Let's do another one. In this example, the first 3 octets are all ones, but the last octet has 2 ones and 6 zeros. So let's count the number of ones in this subnet mask. There are 8 in the first octet, 8 in the second octet, 8 in the third octet, and 2 that are in the fourth octet. If we count all of those together, we have 26. So the CIDR block notation of this subnet mask would be /26. The /26 means that the first 26 bits of this address are the network part of the address, and the last 6 bits are reserved for the host ID. And here's one more. In this subnet mask, we have the first octet of all ones. The second octet has 4 ones and 4 zeros, and then the third and fourth octets are all 0. Since we are counting number of ones, we have 8 in the first octet and 4 in the second octet. And if you count those together, the subnet mask in CIDR notation would be a /12. That means that the first 12 bits are for the network ID, and the last 20 bits would be for the host ID. We've looked at the subnet mask in binary, and we've calculated CIDR block notation, but we often refer to the subnet mask as a decimal value. If we were to convert these binary subnet masks into a decimal value, there are only a certain number of these that you would run into. For example, all zeros would obviously be a decimal 0, but anything that starts with a binary of 1 and the rest zeros would be a decimal of 128. If there are 2 ones, it's 192, 3 would be 224, and so on. This means that you could create a chart that shows all 8 of the bits within a single octet and what the decimal equivalent would be. We can now use that chart to calculate the CIDR block notation and what the decimal representation of that subnet mask would be. So let's look at a subnet mask of all ones in the first octet. There are 4 ones in the second octet, and the rest of this would be all zeros. If you refer to our chart, you can see that all ones is 255, 4 ones and 4 zeros would be 240, and then of course all zeros would be 0. And if we were to count the number of ones, we know that correlates back to a /12. So a /12 CIDR notation is the same thing as 255.240.0.0 in decimal notation. And of course, since there are 12 ones, the network section is 12 bits in length, which leaves the remaining 20 bits available for the host ID. Let's look at a subnet mask we've not seen yet. This one is all ones in the first octet, all ones in the second octet. There are 3 ones in the third octet, and of course the rest of this is zeros. If we look at our chart, we can see that of course all ones is 255, and in the octet that has 3 of these ones, we refer to the chart, that is the same as 224 in decimal. And obviously all zeros in binary is the same as 0 decimal. If we then count the number of ones in all of these octets, they all add up to 19. So your CIDR block notation would be /19, which corresponds back to the decimal representation of 255.255.224.0. This of course means that the network part of this address is 19 bits in length, and the host section is 13 bits in length. Of course, we can do this in reverse as well. Let's say that we have a subnet mask that's been given to us as a /26 in CIDR block notation. If we were to write this out in binary, that means that we would have all ones in the first 3 octets and 2 ones in the last octet. And if we would refer back to our chart, all ones would obviously be 255, and the last octet that has 2 ones correlates back to a 192 in decimal. So a /26, where your network ID is 26 bits in length and the host ID is 6 bits in length, is the same as a /26 in CIDR block notation, or 255.255.255.192 in.
Oh snap!
Let's do another one where we
Woo-hoo! Look at Charles on the road, boy. He's doing his little dance. Yeah, congratulations.
Third octet has 4 ones and 4 zeros, and of course the last octet will be all 0. We refer to our chart, and we know that the decimal version of that binary subnet mask will be 255.255.240.0.
Yeah, I'll update your score, but as far as CompTIA is concerned, you should see a reflection in your certification tomorrow in your dashboard.
Which leaves us 12 bits available for host IP addresses.
Good job. Oh, for those that are just making it back, make sure you clock in, and I'll adjust your time, give you your time back. So make sure you clock in.
It was designed to optimize your battery life, so it works longer without a charge, and in places without a charger.
Look, I think something's happened to us.
What are you?
It's me, Mom.
You're not my mother.
Yes, I am.
Get away, you clone freak!
Don't you use that tone with me.
Oh my God, you are my mother.
And you're not who you think you are.
Look at me!
I know, we seem to be in.
I'm old!
I beg your pardon.
Oh, I'm like the Crypt Keeper!
Okay, that's enough.
I want my body back!
And I don't want mine. My wedding's tomorrow. Oh my God, my wedding.
In this video, we're going to look at a detailed calculation of subnets and hosts using IP version 4. If you stumbled across this video, I highly recommend you go back and look at our video on binary math, classical subnetting, and IPv4 subnet masks. As we've been going through these subnetting videos, you may be asking yourself, why do we have to go through this process of calculating IP addresses, their mask, looking at default gateways, and understanding what the first and last available IP address might be? Well, that's because it would be functionally impossible to have one device that would know where every other device in the world might be. Instead, we create smaller networks and we build routers that are able to get information between all of these smaller networks. This allows us to communicate to anywhere in the world without knowing exactly where that destination location might be. We simply send out the packet, and the routers every step of the way allow us to get that information to the final destination. Well, this means that we need to create these smaller networks, and we do this by using a process known as VLSM, or Variable Length Subnet Masks. As the name implies, these subnet masks are not like the class-based networks that we looked at earlier, which have a very fixed number of bits in the subnet mask. Instead, we can create a subnet mask that has a different number of bits on every network, therefore creating a variable length of a subnet mask. This means you, as the network administrator, can build a network that is exactly the right size with the right number of networks and the right number of hosts. And you have complete control over what the subnet mask might be for that network. This is a lot like cutting a pizza into smaller pieces. How many pieces do you need in the pizza? Should the pizza be cut in 2 pieces? Should it be 4? Should it be 8? Or should it be even more than that? If we apply this to IP, we can look at a Class A network, which has 10.0.0.0 and a subnet mask with a /8. But if we wanted to cut that pizza into smaller pieces, we might have a subnet mask of a /24 or even a /26. Since we're using a different number of bits than 8 in the subnet mask, we're using a variable length subnet mask that we can define to be whatever we'd like. Let's perform some of this variable length subnet masking, but let's first look at the default subnet mask for a Class A address. This would be 10.0.0.0. The default is Class A, since that starts with the number 10, and the default subnet mask for that would be 255.0.0.0. This would be the default subnet mask if all we did was have classful addressing. If you were to look at this classful address in binary, the first 8 bits would be 1, and the remaining bits would be 0. In decimal, that means it would be 255.0.0.0, and if you were to use the CIDR block notation, this would be a /8 subnet. This means that the network bits would be those first 8 bits of the address, and the host bits would be the last 24 bits of the address. Since this is a /8 subnet mask, we are drawing our line after those first 8 bits of the subnet mask. But in reality, of course, we could pick a different number of subnet bits. We just need to decide what works best for our network. For example, let's draw our line right after the 3rd octet. This means that we still have our default first 8 bits as part of that Class A address, but we're going to borrow the middle 16 bits as what we call our subnet bits. This means those subnet bits would now be turned into 1, and the host section of the IP address would shrink down to 8 bits. This means that the decimal subnet mask would be 255.255.255.0, and the CIDR block notation for this new subnet mask would be /24.
Cybersecurity today is so messy and expensive. And why does it take so long? It really shouldn't be that. Get started with Sola, the studio where you can build any security app. Whether you're the security person or just the person tasked with security, tie together some loose ends or build up your security stack. You fit Sola to your needs. It's simple, quick, and free. Get security done with Sola.
I think I like sports now.
No way. The gecko was just spotted down the street.
I've always wanted to meet him. Ever since Geico's 24/7 emergency roadside service got us out of a jam.
Sounds like you got more than just savings, my dudes.
So do we know you?
Oh, I'm just a stranger who loves friendly service and American football.
Okay. Something to drink?
Oh yes, hot tea would be lovely. And a root beer with lots of ice.
You know, you kind of look like someone.
Get more than just savings. Get more with Geico.
My cousin Daryl.
Oh, he does look like Daryl.
We've been doing a lot lot of these calculations in binary, and then we've been converting that binary back to decimal. But that process tends to take time, and one of the faster ways to perform these calculations is to look at a list of the powers of 2. For example, you can look at 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and so on. If you want to calculate the number of subnets and the number of hosts, you can calculate the number of subnets as 2 to the number of subnet bits, and the number of hosts per subnet would be 2 to the number of host bits minus 2. That subtraction for the 2 means that we are subtracting the number that we would use for our network address and the number that we would use for our broadcast address. Everything in the middle would be our host addresses. So let's now use this chart with our powers of 2 to calculate the number of subnets and the number of hosts per subnet. Let's take the IP address of 10.1.1.0/24. If we perform our calculation in binary, we would write out all 24 of those bits as 1s, and the last 8 bits would be 0. The default for a class A address such as this one, though, would normally have our network address as the first 8 bits. But we are moving that line another 16 bits over so that we are borrowing an additional 16 bits for the subnet. That leaves us with 8 bits left over for the host. If we were to calculate the number of subnets using these powers of 2, we would take 2 to the number of subnet bits. And since we have 16 subnet bits, 2 to the power of 16 is 65,536. If we were to calculate number of hosts per subnet, it's 2 to the number of host bits minus 2. We have 8 host bits, which means 2 to the 8 minus 2 is 256 minus 2, or 254. So for this IP address of 10.1.1.0/24, we can have a maximum number of subnets of 65,536, and on each of those subnets, we can have a maximum of 254 devices. Let's calculate another one. We'll look at an IP address of 192.168.11.0/26. If we were to write out that /26, you can see there are 26 ones. That leaves us with 2 ones in the last octet, and we have 6 zeros left over at the end. If we calculate the class of this address, we look at the first octet, which is 192, which means this is a Class C address. That means it has a total number of 24 bits as the network address by default.
How can I finish
we
off?
borrowed a couple of extra bits into the last octet, so there are 2 additional bits available that we will call our subnet bits. And then, of course, we have the last 6 bits available as the host bits. Let's perform our calculation again. To calculate the number of subnets, we use 2 to the number of subnet bits. We have 2 bits left over as the subnet bits. 2 to the second power is 4. To calculate the host per subnet, we have 6 bits, so we take 2 to the first power and subtract 2 from there. That means we have 64 minus 2, or 62. So for this IP address of 192.168.11.0/26, we can create a total of 4 subnets, and on each of those subnets, we can have a total of 62 devices. This same process works with any type of subnet mask. Let's take, for example, 172.16.55.0/21. If we looked at this in binary, we would have 21 ones, which means we have 8 in the first octet, 8 in the second octet, and 5 ones in the third octet. Everything else, of course, would be zeros. And if we look at this IP address, it starts with 172, which by default would be a Class B address. So by default, the first 16 bits would be your network address. We borrowed some additional bits, in this case, 5 additional bits to be our subnet bits, and then everything left would be our 11 host bits. Performing our calculation again, we have 5 subnet bits.
Y'all make sure y'all get in the break.
Subnets, it's 2 to the 5th
Take 10
power,
minutes.
or 32. We have 11 host bits left over, so if we calculate that as 2 to the 11th power minus 2, that would be the same as 2048 minus 2, or a total of 2046 devices. So for this IP address of 172.16.55.0/21, we can have a total of 32 subnets, and on each of those subnets, we can have a maximum of 2046 devices. If you use this powers of 2 to perform these calculations, it can be a very quick way to determine what the number of subnets might be and what the host per subnet might be. But there are some shortcuts available that might get you to these values much faster, and in the next couple of videos, we'll give you some different options for calculating this process using those shortcuts.
CompTIA certification is too expensive? Let me show you some math. A CompTIA certification is going to make up to $15,000 more than somebody who's non-certified. And $15,000 divided by 12, $1,250. That's more than $1,200. And that right there pays for your certification in 2 weeks. And if you're still not convinced, check out what this student said.
I was stuck at a help desk making $48,000. 6 months after getting security plus certified using Dion training, I landed a security analyst role making $78,000. Best investment I ever made.
And Dion's exam vouchers are 10% lower than CompTIA's price. And when you add our Take 2 insurance, you're saving more. And the real question is not, can I afford this certification? It's, can I afford not to get it? Dion Training. Invest in yourself today at diontraining.com and get certified faster.
Bath and Body Works and Disney have a new collection to bring out the villain in you. And I'll help you pick your potion. Apple for plum, Goose Fix for your villain of choice. A crown fit for a queen, or 7 sinister horns. A royal castle or a magical forest realm. Disney's Maleficent, the evil queen. And now you let sense lead you into your villain era.
If you've been with us with the videos just prior to this one, then you've learned a lot about subnetting, masks, CIDR block notation, and other important fundamentals when it comes to subnetting via IP version 4. All of that work has brought us to this point where we can start to answer questions like this one. Here's a network layout, and it says, here's your IP address assignment. We've been given the IP address of 192.168.1.0/24. And this says we need an IP addressing scheme with more than one network address that can support 40 devices per subnet. That is the optimal number we're looking for, and we need to determine how to subnet this network address to be able to get 40 devices per subnet. Now you could of course write out all of the possibilities in decimal and binary and be able to calculate what the differences are with the number of networks and the number of hosts per network. For example, if you look at the default subnet mask that we were given, which is 255.255.255.0, you can see this is the binary representation of that subnet mask and the CIDR notation, which is a /24. That gives us one single network with 254 hosts per network. If we borrow 1 bit from the host side so that we are at 255.255.255.128 as our subnet mask, or a /25, we would be able to create 2 networks with 126 hosts per network. We are getting closer to that number of 40. Let's keep going by borrowing another bit so that our subnet mask is 255.255.255.192, or a /26. This allows us to have 4 networks with a total of 62 hosts on each of those subnets. This is certainly getting close to 40, but let's go one more step to see if we're getting even closer to that 40 value. The next step would be to borrow 1 more bit from the host side. So now we're borrowing 3 subnet bits, which means our subnet mask is 255.255.255.224, or a /27. If we subnet in this way, we can have a maximum of 8 networks, but it would only allow for 30 hosts per network. This means that the optimal subnet mask, if we're looking for a total of 40 devices per subnet, would be the next one up, or the /26, which would give us 4 networks and a maximum of 62 hosts per network. Now we can certainly speed this process along by performing a calculation based on powers of 2. Let's look to see how we might do that. We have a starting IP address of 192.168.1.0 and a subnet mask of 255.255.255.192. And based on this information, we can show the network address and the subnet mask in binary. And you'll notice in the subnet mask, we have the default number of bits for that address, plus the 2 extra bits that we borrowed from the host side. Visually, you can see where the 24 subnet bits might be, the 2 extra bits we borrowed for the subnet, and the 6 bits that are left over on the host side. If we were to now calculate the number of subnets and the number of hosts per subnets using this powers of 2 formula, we would take 2 to the second power, because the second power would be 2 bits, and that would be a total of 4 networks. We would determine the number of hosts per subnet by taking those 6 host bits that are left over at the end and calculating 2 to the 6th power minus 2, which would be 64 minus 2, or a total of 62 hosts per subnet. This is a relatively straightforward way to calculate the number of subnets and the number of hosts per subnet, but it requires you to perform a binary conversion and then count the number of bits to be able to calculate what that total might be at the end. There are some shortcuts that we can use, and in this video, we're going to look at a shortcut that uses the magic number method. These calculations are intended to give us 4 separate pieces of information. First, we need the network address or subnet ID. This would be the first address in the subnet. We also need a broadcast address. This is the last address in the subnet. We need the first available host address. This is an address that we can assign to a device on this subnet. And then we need the last available host address. We need to be able to calculate these as quickly as possible. Now, obviously, we could calculate this by converting everything to binary, looking at the subnet bits, and then calculating for every possible scenario what this particular network address might be and the subnet mask for each one of these. And for this particular IP address, where we determined there were 4 separate subnets, these are all the calculations that we would need to do to be able to calculate all of that information for all 4 of those subnets. You can see looking at this screen that there are a lot of separate binary to decimal conversions you'd have to do just to calculate those specific details for all 4 of those subnets. We can simplify this process by using the magic number shortcut. This allows us to perform subnet calculations very quickly, and very often we can do all of these calculations in our head. There's still a little bit of math involved with the magic number method, but it's limited to powers of 2 and some very simple addition and subtraction. You could even create a few charts that might help you with the process, but once you get accustomed to using this method, you'll find that you memorize very easily what's in the charts. You may not have to write them down at all during your exam. One chart that might help you is a chart that easily converts between a CIDR block notation and the decimal subnet mask notation. You can see an example of this might be to use a /9 is 255.128.0.0, /10 is 255.192.0.0, and so on. You will notice that there are some patterns after a while. For example, a /9 has the 128 as the number that is a bit different than a 0 or a 255, and a /17 also has a 128. So we could write this chart in a simplified form that shows a /9, a /17, and a /25 use the 128 as the decimal value. In the magic number method, we have a number of different tasks that we perform based on the octet that we're working with. So we might want to modify this CIDR to decimal chart to have something that's a little bit different. For example, if you wanted to see the CIDR notation for interesting octet 2, you can see it ranges from a /9 through /16. The CIDR block notation for interesting octet 3 would be /17 through /24, and the CIDR block notation for interesting octet 4 ranges from /25 to /30. You notice that we don't use /31 by default because it doesn't leave any room for any hosts on the subnet, and we don't use a /32 because that leaves 0 bits available for any hosts. For each of these columns with the CIDR block notation, you'll notice there is a magic number, and in a moment we'll learn how to use that magic number value. We can also put in this chart the subnet mask for an interesting octet, and you can see those mask values are also listed as well, starting at 128 and working all the way up to 255.
At Sprouts, our wide open layout invites you in.
I know that.
With healthy around every corner.
Optionally, you can also create a host range chart where you can take an address block and then separate out what the differences are for that particular block. For example, an address block of 128 splits the network into two different pieces, 0 through 127 and 128 through 255. An address block of 64 hosts per block would be 0 through 63, 64 through 127, and so on. And you can continue this process with a host block of 32 hosts, 16 hosts, 8 hosts, and so on. So let's see how the magic number method works. It's a series of steps, and once you go through these a couple of times, they become very second nature. The first step is to convert the subnet mask to decimal if it's not in decimal already. From there, we need to identify the interesting octet. We'll talk about the interesting octet in just a moment. We then need to calculate the magic number, which is 256 minus the value of the interesting octet. We could then calculate the host address based on that, identify the network address, which would be the first address in that range, and then identify the broadcast address, which would be the last address in that range. So now let's take an IP version 4 subnetting problem and answer this problem using the magic number method. We'll start with this IP address at 165.245.77.14, and we've been given a subnet mask of 255.255.240.0. Our first step would be to put the subnet mask into the chart. You can see that it's already in decimal form, so we simply need to copy it over with 255.255.240.0. We can then also fill in the IP address that we've been given, which is 165.245.77.14. From here, we can start to make some decisions about what to put into this chart. For example, if the mask is 255, you simply copy the IP address down. So in this case, the mask is 255 in the first octet, so we're going to copy that down, which means our subnet ID will be copied down with the same number that's in the IP address row. Let's perform that same task again with the second octet. It is also 255, so we're going to copy that through. This 245 then will be brought down into the subnet ID row. We no longer have any octets with the 255, so our next step will be to look at any octets where the mask is 0. And if the mask is 0, we bring that 0 down to the subnet ID row. In this case, our last octet does have a 0, so we're going to copy that 0 all the way down and put it into the subnet ID row in the last octet. In our example, the subnet mask in the third octet is a 240. That is obviously not 0 and not 255, so that octet is our interesting octet. Now that we know the interesting octet, we can use that to calculate the subnet ID value for that particular octet. To be able to do that, we need to subtract the interesting octet subnet mask from 256. In our interesting octet, the subnet mask is 240. So if we subtract 240 from 256, we have the value of 16. This means our magic number is 16, and there would be 16 hosts available on that particular subnet. If we put our chart at the bottom that shows the 16 different hosts that you would have and the delineation between each one of those subnets, you can see that we have a range between 0 and 15, 16 through 31, 32